Okay. Chalo. So these topics I am going to discuss in this. First is periodic table. Periodic table. Okay. So let's quickly brief the important concepts of periodic table. For example, if you want to find the radius of any atom, then we are taking help of bond length, and based on that bond length, we can define radius like covalent radius, metallic radius, or van der Waals radius. As per the IUPAC rules, van der Waals radius cannot be compared with the covalent radius or metallic radius of other. Means VWR of one atom is not compared with the CVR or MR of another atom. Bond length can be measured by X-ray diffraction technique, electron diffraction technique, or by the spectroscopic methods. Generalized trend for S and P block, when we are moving top to bottom, radius increases. We have one exception here, that is aluminium gallium pair, where trend is reversed. Actually, both are not exceptional. Only gallium is exceptional. It is only for memorization. In aluminium gallium pair, in this aluminium gallium pair part, trend is going to be reversed. As we move left to right in a period, radius decreases because Z effective increases, so radius decreases. For example, let's say we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. In this case, for neon, we have van der Waals radius, so I will ignore it. And for others, I can generalize. As we move left to right, Z effective increases, and so radius decreases. Okay. In case of neon, we have van der Waals radius only. So if they are saying, comment about the van der Waals radius of VWR of neon and CVR or MR of others, then better answer is ignore, or this comparison is not allowed as per the IUPAC. If they are saying strictly no, I won't answer, even though it is not allowed as per IUPAC, then you can say VWR is more than others. Technically, this is the incorrect information because one is VWR and the others are CVR and MR. CVR, MR, they are close to the actual value. That's why, as per the IUPAC rule, first preference is don't compare VWR of one atom with the CVR or MR of another. Okay, so is it possible to have VWR for other cases? Yes, it is possible for other cases also. Means I can have VWR from lithium to neon, all have VWR. But in case of neon, we have only VWR. Other cases we have VWR plus either CVR or MR depending on the condition. One point I said for the top to bottom of SN block, like if you're moving top to bottom, radius is increasing because N shell number is increasing. Exception is aluminium gallium pair. So if I'm writing radius for the boron family, boron, aluminium, gallium, indium, and thallium, in this part I will reverse the trend of radius for aluminium gallium pair. For others I will write as per the normal concept. Normal concept, top to bottom radius increases, so I will increase it, but in this aluminium gallium pair I will reverse the trend. I will reverse the trend means I will write aluminium is slightly more than the gallium. So based on this I can write the radius value here, radius order boron, gallium, aluminium, indium, and thallium. Okay, now I had two important points. First point, in this case I am observing radius of gallium become less than aluminium. If someone asking why, so you can answer simply due to the poor shielding of d electrons. It is having d10 configuration, and that is why it is having lesser radius. Second important point, this is the trend of atomic radii. When you are writing atomic radii, we are observing gallium is having value lesser than the thallium. But if you are observing at ionic radii, for ionic radii, they are following regular trend, means regular increase from boron to thallium. So ionic radii, it is regular trend. Ionic radii is having regular trend for the group 13 also. Regular trend for group 13 also. This is the radius. Next is ionization enthalpy. If you are finding ionization enthalpy, if you are trying to find the ionization enthalpy or ionization energy is defined at low Kelvin temperature, ionization enthalpy can be defined at any temperature. Okay, that is the part of thermodynamics. For now, just focus on the trend. As we move, if I am observing S and P block, as I am moving top to bottom, what is happening? N is increasing. So distance between nucleus and means kind of, I guess, radius increasing, or distance between nucleus and electron, which I am going to remove, is increasing, and that is why ionization enthalpy is going to decrease. For this concept, ionization enthalpy is going to decrease from top to bottom in case of S and P block. We have two important exceptional cases. One is in group number 13, few elements. So I'm writing group number 13 and means boron family. Group number 13 means boron family. And in carbon family, tin and lead. This pair is having exceptional ionization enthalpy trend. For example, in case of boron family, when I'm writing the ionization energy trend, method is very simple. You can make this kind of W. For the ionization enthalpy trend of boron family, you can make this kind of trend, means boron, aluminium, gallium, and helium. In this way, you can memorize. So whenever you are solving ionization enthalpy of boron family, you have to draw this W. Okay, na? So here you can observe maximum ionization enthalpy for boron, then for thallium, then gallium, aluminium, and least for the indium. In this way, you can memorize the trend of ionization enthalpy for the boron family. Another is, if you are observing carbon family, means group number 14 or carbon family, then carbon, silicon, germanium, tin and lead. This part is exceptional. So here we have to write the opposite trend. So general trend top to bottom ionization enthalpy decreases. So decreases, here I will write opposite trend, means increases. So trend will be what? Carbon, silicon, germanium, lead and then tin. So if someone is asking why lead is more, answer is because of poor shielding of F electrons or due to the lanthanoid contraction. This is the trend of ionization enthalpy in S and P block. So I said here radius trend. For radius trend, what I said, exceptional is aluminium gallium pair. Actually gallium is slightly lesser, aluminium is not exceptional. Gallium is slightly less than the aluminium because of the poor shielding of d electrons. While in case of ionization enthalpy, I said two cases are exceptional: boron family, few elements, and group 13, group carbon family, tin and lead pair. So actually in this, lead is becoming exceptional and having exceptionally high value due to the poor shielding of F electrons. Now come to the electron gain enthalpy and electron affinity. You're knowing electron gain enthalpy means I'm giving electron to the isolated gaseous atom and is becoming anion. In this case, whatever energy is required or released is named as electron gain enthalpy. First electron gain enthalpy means when I'm giving first electron to the atom, first electron gain enthalpy can be positive or negative. Positive means process is endothermic and negative means process is exothermic. Memorize endothermic cases of S&P block, other cases are obviously negative. So positive cases are beryllium, magnesium, nitrogen and noble gases. These are the cases where electron gain enthalpy first is positive and other cases it is negative. If I'm going for the second electron gain enthalpy, means A minus and E minus, means now it is anion who is binding with the electron. So in this case minus minus they are repelling and are binding electron against the repulsion. This is always going to be positive. So second electron gain enthalpy, third electron gain enthalpy, they are always going to be positive. Why they are always positive? Let's say you are solving third electron gain enthalpy. Then you will give electron to the 2 minus. So now this is minus charge and this electron is also minus charge. Minus minus they are repelling and you are binding electrons against the repulsion. So obviously in this case energy is required. So first electron gain enthalpy value may be positive or negative. Positive for beryllium, magnesium, nitrogen and noble gases. Other members of S&P block, they are having negative value of the electron gain enthalpy 1. Second, third onwards, all the electron gain enthalpies are always positive because in this case you are binding electron against the repulsion. Okay, now come to the trend. Electron, if I am solving electron affinity, so electron affinity is denoted by symbol AE. This is the standard symbol for the electron affinity. So electron affinity AE is equal to minus of electron gain enthalpy minus 5 by 2 RT. This is the formula here. Electron affinity is equal to minus electron gain enthalpy minus 5 by 2 RT. This is for the atoms or isolated gaseous atoms. Okay, so based on this we can conclude if electron gain enthalpy value is negative, electron affinity is going to be positive. Okay or not? Come to the trend. Electron affinity actually is telling that what is the tendency of it is giving information about the tendency of atom to bind with the electron. Electron affinity is the most irregular trend in the periodic table. Electron affinity is the most irregular trend in the periodic table. So in this case, simply we can go for the trick. If you are solving second period electron enthalpy, then memorize by the trick NB LIC office. What is the trick here? NB LIC office. So NB LIC office. NB LIC office. So it is neon, then beryllium, nitrogen, boron, LIC office. This is the increasing order of electron affinity. Based on this, we can think about the third period also. Like below neon, what we have argon, below beryllium, what we have magnesium, below nitrogen, what we have phosphorus, below boron, aluminium, lithium, sodium, below carbon, silicon, below oxygen, sulfur, and below fluorine, chlorine. In this way, you can write the trend. Only one change will happen, that this phosphorus will be placed before silicon. Phosphorus is placed before silicon. Okay or not? So in this case, what is concept here, or what is the trick here? Electron affinity is the most irregular periodic trend. It is better memorized by the trick. Trick is what? NB LIC office for the second period. So neon, beryllium, nitrogen, boron, lithium, carbon, oxygen, and fluorine. Third period is same as second period, only one small change is there. Phosphorus is kept before the silicon. So you can memorize like this also. Puspa is before Sivalli. Puspa is behind Srivalli. In this way, Puspa. Phosphorus Puspa and silicon Srivalli. So Puspa is behind Srivalli. In this way also you can memorize it. Okay, this is the trend of electron affinity. One more point. If you are solving ionization enthalpy in a period, for example, second period. So elements are lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Okay, these are the elements. Whenever you are solving ionization enthalpy in a period, always write elements with the electronic configuration, or at least write the configuration of subshell from where you are going to remove the electron. So for example, here I am writing lithium to neon with the configuration. So in case of lithium, I will remove electron from 2s1. This is going to be 2s2. This is going to be 2p1, 2p2, 2p3, 2p4, 2p5, and 2p6. After writing the elements with the configuration, highlight only two configurations, S2 configuration and P3 configuration. What to highlight? S2 configuration and P3 configuration. S2 will dominate over next means P1, and P3 will dominate over P4. Always remember, S2 can dominate over P1 and P3 can dominate over P4 only. Like S2 cannot dominate over P2, or P3 cannot dominate over P5. P3 dominates over P4, S2 dominates over P1. In this way, we can write the trend of ionization enthalpy. So answer will be what? Lithium, boron. Beryllium is going ahead, so it is beryllium, carbon, oxygen, nitrogen. Nitrogen is now more than oxygen, then fluorine, and then neon. In this way, it is written for the trend. It is trend of first ionization enthalpy of the second period. If you want to write second ionization enthalpy, then remove one electron and write the configuration. For example, if I am solving second ionization enthalpy for the second period, elements are lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. In this case, what I'll do, I'll remove one electron, then we'll write the configuration. So lithium was 2s1. After removing one electron, it become 1s2. This is now going to be 2s1. 2s2, this is 2s2, this is 2p1, 2p2, 2p3, 2p4, and 2p5. What method I said? Whenever you are solving ionization enthalpy in a period, write elements with their configuration. After writing configuration, you clearly observe here beryllium to neon. In these cases, electrons are removed from the second shell. Am I right or not? While for lithium, I am removing from the first shell. So it is very obvious thing, ionization energy of second of lithium is extremely high as compared to the others. And for others, go for the same concept, highlight two configurations, S2 configuration and P3 configuration. S2 dominates over P1 and P3 dominates over P4. S2 dominates over P1 and P3 dominates over P4. So based on this, I can say कि beryllium, carbon, increasing trend I am writing, boron is going ahead, so boron, nitrogen, fluorine, oxygen, neon, and lithium is maximum here. It is second ionization enthalpy. And with the same logic, you can solve third and fourth ionization enthalpies also, but usually they are asking first and second. And whatever concept I said for the second period, same is applied for the third period also. This is the ionization enthalpy trend. For electronegativity, you are knowing it is the tendency of atom. It is the tendency of atom to attract the bonded pair of electrons. Am I right or not? So electronegativity is most regular periodic property. I'm not saying it is completely regular, most regular. I'm saying among all periodic properties, En is the most regular periodic property. It is having less number of exceptions. Okay. Now come to the questions. given in NCERT. So this is the generalized, this is a brief idea about the periodic table. Now go for the questions. Okay, problem number 3.1. They are asking about the IUPAC name of element with atomic number 120. 120. Atomic number 120. So if it is written 120, 1 means un, 2 means by, and 0 means nil. So UBN. In this way we can write. You know, if it is 0, nil, 1, un, 2, by, 3, try like that. We can write the 4 quad. Okay. So in this we can write the IUPAC name. So it is 120. So for U, 1 I can write U. First is capital letter. Then 2 by and 0 nil. So UBN. So name can be written as unbinilium. Unbinilium. Okay, this is problem number 3.1. Move to the next problem. Problem number 3.2. How would you justify the presence of 18 elements in the fifth period of the periodic table? They are asking ki fifth period of periodic table is having 18 elements. How you will justify this point? So now, in case of fifth, I am saying fifth period. Written here, fifth period. It means n value is 5. Highest principal quantum number is 5. And if highest principal quantum number is 5, then think what orbitals are present there. Okay or not? So in case of fifth, we have 5s, 4d and 5p. 5s, 4d and 5p. So based on this, we can means 2 possibilities, d means 10 possibilities, and p means 6 possibilities. And that's how we can have how many elements? 18 elements. So in case of fifth year, what is present there? 5s, 4d, 5p present, and based on this we can say for s we can have 2 possibilities, for d obviously in s we can place 2 electrons, so in s orbital we can place 2 electrons, so 2 possibilities are there. For d I can place, for d subshell I can place 10 electrons, maximum 10 electrons, that's why we have 10 possibilities there. And likewise for p I have 6 possibilities. If you add all of them it is going to be 18, and that's how we can justify in fifth period we have 18 elements. Okay, that's what they're writing here. You can observe the order of which energy of this is 5s, 4d and 5p, and based on this they are justifying 18 elements in the fifth period. Next problem, problem number 3.3. Question is, element number 117 and 120 have not yet been discovered. 117 is now discovered. It is a synthetic element, but okay, they are saying so we have to follow it. And 120 have not been discovered. In which family group would you place these elements and also give the electronic configuration of each case? So now, once you know the position in periodic table, you can easily think about the configuration part. So now listen. You are knowing, if I am writing periodic table, they are saying 117. So knowing the last member like helium, neon, argon, krypton, xenon, radon, and last member oganesson. Atomic number of oganesson is what? 118. So obviously 117 is before this. Before this means this is group number 18. Before this means group number 17. Means halogen family. Is it clear or not? So this group 117 is actually before oganesson. So now halogen family general configuration is what? NH2NP5. So same we can write for this also. Is it clear now? This belongs to 7th period. Sir, how will know? But helium belongs to which period? Second, third, fourth, fifth, sixth. Okay. Helium belongs to first period. Sorry. Helium 1, 2, 3, 4, 5, 6, 7. Oganesson belongs to 7th period. It is just before this. Means it is also 7th period. So we can write configuration here 7s2, 7p5. Generalize. Before that I can write noble gas also. Okay. Now another is given 120. So go for the same concept here. Same concept here. Helium to oganesson. Atomic number of oganesson is 118. And if I'm writing first, this is helium is last one, 18th number. Helium is last one, group number 18th, and I'm writing first one now. So I'm writing hydrogen here, hydrogen, lithium, sodium, potassium, rubidium, cesium and francium. Okay now. So in this case, voice coming, just confirm once. Voice is coming or not? Confirm once please. Voice is coming or not? Quickly answer. Okay. So now in this case, hydrogen 1, 2, 3, 4, 5, 6 and 7. This is your group number 1. Now what is given? So this will be group number 2. What is given here? 118 is last member here. This is 118. So 118 is here. 119 will come here and 120 will come here. Means 120 belongs to group number 2. And for group number 2, generalized configuration is what? NS2. Based on this, we can write this also. So this kind of question can be solved by this method. You can write first group or 18th group, and based on this, we can locate the position of the given element. For example, if they are giving 120, which is going beyond the current form of periodic table. Okay, now. So obviously, this is 7th period. This will go in period number 8. Means we have to design, we have to extend the periodic table, and accordingly, we have to place it if it is existing. Okay. Okay. Next question is, consider the atomic number and position of the periodic table. Arrange the following elements in the increasing order of their metallic character. Few elements are given here: silicon, beryllium, magnesium, sodium and phosphorus. It is very easy question. You are knowing sodium belongs to first A. Sodium belongs to first A, and in first A, metallic character is very high. And this is sodium. So we can write here sodium is maximum here because belonging to first A. First elements are having ionization enthalpy lower than other members in general. That's why it is having, they are having high metallic character. So sodium, before sodium we can write second A means magnesium. Okay, then we can write beryllium. Out of beryllium, magnesium, who is having more metallic character? So obviously beryllium has high ionization enthalpy, so metallic character is less. Magnesium is having lesser ionization enthalpy, so metallic character is more. So I can write beryllium here. Then before that I can write silicon and then phosphorus. Is it clear or not? So we can simply answer the metallic character here. So let's check answer quickly. They are writing here maximum for sodium. They are writing maximum for sodium first A. Then these two second A. Phosphorus, silicon, we can solve left right as we are moving. Metallic character decreases or non-metallic character increases. Okay, next question. Next question. Okay, I said one concept ki as we are moving left to right, and radius is going to decrease. That's what you can observe. Lithium, beryllium, boron, carbonate, oxygen, fluorine, radius is decreasing. Okay or not? One more important point, all first elements are having radius greater than the all group number 17 means halogens. All first, like lithium to cesium, all first are having radius greater than all halogens, fluorine to iodine. In fact, you can observe here, lithium is having radius greater than the radius of iodine. This is also very important fact. Okay, next is, which the following will have the largest and smallest size. So what we can observe here, sodium, what is given to us? Magnesium plus aluminium and aluminium 3 plus. So we can observe here magnesium plus and aluminium, magnesium 2 plus, Mg 2 plus and Al 3 plus given. Positively charged ions are given, and against them what we have magnesium and aluminium, and they're neighboring elements also. So there is no big difference in the size in terms of the Z effective value. So what we can observe here, they are positively charged, their radius is going to be less than the neutral. I'm not saying this is always true, but in general I'm saying this. Okay, and out of magnesium, aluminium, so knowing as we are moving left to right, it is beryllium, magnesium, boron, it is lithium, beryllium, boron, carbon, like this. Below beryllium what we have? Magnesium, and below boron what we have? Aluminium. So left right radius is going to decrease. Left right radius is going to decrease means magnesium is more than aluminium. With the same logic, now in this case plus 2 and plus 3, obviously plus 2 is lesser, and they are isoelectronic also. So based on what we can say, who is maximum here? Magnesium is more maximum, and who is minimum? Then aluminium 3 plus is minimum. So this is easy question, very easy question. You have to just observe the basics here. Magnesium plus 2, aluminium plus 3. Positively charged are less than the neutral in general. Okay or not? Based on this, we can find the, now separately also we can find magnesium, aluminium. As we move left to right, Z effective increases, radius decreases. Okay, I think this part is also done. Move to the next question. Okay. Now question is, first ionization enthalpy values are given here, and now they are asking whether first ionization value of aluminium will be more close to this, or justify your answer. So I said one concept here, when you are writing elements, when you are solving ionization enthalpy in a period, we have to write elements with the configuration. We have to write element with their configuration. So here what is given? Sodium, magnesium, silicon given. So actually sequence is what? Sodium, magnesium, aluminium and silicon. Sodium, magnesium, aluminum, silicon. So sodium I will write here 3s1, magnesium I will write 3s2, aluminium I will write 3p1 and silicon I will write 3p2. So what concept we are knowing? If it is S2 or P3, highlight them. Here I don't have P3 in this example, but I have S2 there. S2 will dominate over P1. S2 will dominate over P1. So based on this, I can write here sodium, aluminium, magnesium and silicon. Values are given for few elements, like for sodium they are saying 496. For magnesium they are writing 737. And for silicon they are writing 786. So obviously aluminium will come in between sodium and magnesium. So that's what we can find here. For example, here they are saying it is 575. They are asking it is close to 575 or 760. So it is 570 as per the given question, because it is coming between these two values 496 and 737. Basic simple concept you are knowing. Just write elements with the configuration. Highlight two configurations, S2 and P3. S2 dominates over P1 and P3 dominates over P4. Okay. This question also done. Move to the next question. Okay, 3.7. Which of the following will have the most negative electron gain enthalpy and which is least negative electron gain enthalpy? Okay, now in case of electron gain enthalpy, as we are moving top to bottom, if I am observing P block, if I am observing, for example, fluorine, chlorine, bromine and iodine, what is observed? In case of fluorine, it is having high electron density. Fluorine has 7 electrons in the valence shell in the small size atom, and that is why it is having high electron. Because of high electron density, it is providing repulsion to the coming electron, and that's why its electron affinity is lower than calcium. Lower than chlorine. Sorry, electron affinity is less than chlorine. So trend of electron affinity is here: chlorine maximum, then fluorine, and then bromine, and then iodine. Or we can make it one simple concept here: among all elements of the periodic table, chlorine has maximum electron affinity, and second maximum is the fluorine. Okay, so here we can observe they are asking what out of these elements, the one who is having maximum most negative electron gain enthalpy, answer is definitely chlorine. Is it clear or not? This part is also clear to you. One more point: in case of group number first, electron gain enthalpy is regularly decreasing. You can observe here: hydrogen to cesium, minus 73, minus 60, minus 53, minus 48, minus 47, minus 46. It is regularly decreasing. Okay, no exception, nothing. While in case of group number 70, you can observe chlorine is like oxygen family, sulfur is more than oxygen. Third period is more than second period. Chlorine is more than fluorine. But in case of first A, it is not having any kind of exception. Regularly it is decreasing. Means hydrogen has maximum value and then minimum for the cesium. Electron gain enthalpy value. In case of group number 18, electron gain enthalpy, I'm writing here, it is helium, neon, argon, krypton, xenon and radon. Means what we are observing: minimum for helium and maximum for neon. Which value? Positive value. I'm saying here, I'm not saying electron affinity value. Positive value. Like you can observe, helium is plus 48 and neon is plus 116. So neon is plus 116, means it is absorbed value. If absorbed value more, means electron affinity less. If in case of negative electron gain enthalpy, if value is negative, more negative value, more electron affinity. If electron gain enthalpy is negative, more negative value, more electron affinity. For positive case, more electron gain enthalpy means less electron affinity, because more energy required here. Now, more energy required means more unfavorable for the binding of electron. So concept is very simple. Helium, neon, argon, krypton, same as per the NCERT data, then xenon and then radon. In this way, you can memorize the electron gain enthalpy trend of the group number 18. Is it clear or not? It is electron gain enthalpy trend. It is positive value. So electron affinity trend will be opposite of this. Okay or not? Next is electronegativity. Values are given there. Question number 3.8. Using the periodic table, predict the formula of compound which might be formed by following pair of elements, silicon and boron. So in case of silicon, it is belonging to group number 14. Silicon belongs to group number 14. So it is having generally tendency to make 4 bonds. And bromine will make 1 bond, so it will be SiBr4. SiBr4. Next is given there aluminium and sulfur. Aluminium is +3 and sulfur is -2. So based on this, we can go for crisscross and we can write formula here. Al2S3. Al2S3. Got the concept now? In this way, you can write formula. Next question. Not required. Just give me coffee only. Only coffee. Okay. Next is. Next. One more fact, very important fact. Just go through this. Observe here. You can observe for lithium, beryllium, sodium, magnesium. They are writing metallic radius and ionic radius. Metallic radius and ionic radius. What we are observing here. When I am comparing lithium and magnesium. When I am comparing lithium and magnesium for the atomic radii or metallic radii, who is more? Magnesium is more. Who is more? Magnesium is more. But when you are comparing ionic radii, lithium versus magnesium, who is more? Lithium is more. Slightly more. There is no big difference. So this is also very important fact. When you are observing atomic radii of lithium, magnesium is more than lithium. But when you are observing ionic radii, lithium is more than magnesium. Means actually lithium plus and magnesium 2 plus. This is there. Lithium plus having more radius than the magnesium 2 plus. There is a small difference. Values are very close. That's why they are having diagonal relationship also. But this is important fact. Atomic radii of magnesium is slightly more than lithium, and while ionic radii of lithium is more than magnesium. Okay or not? Next is here question is, are the oxidation state and covalency of aluminium in this complex are same? So let's find the oxidation state. What is given here? AlClH2O5 2 plus. So aluminium oxidation state, I am assuming X, chlorine -1, water 0 charge is equal to +2. Here value is coming +3, means oxidation state of aluminium is +3. Oxidation state of aluminium is +3. Now in case of covalency, how many bonds are formed in the surrounding of aluminium? 1 with the chlorine and 5 with the water. What is given here? ClH2O5. 1 with chlorine and H2O will make 5. You are knowing H2O is a monodentate ligand. So covalence is going to be 6. So obviously they are not same in this example. Next question. So the chemical reactions with the water, that Na2O is basic oxide and Cl2 is acidic oxide. So you are knowing Na2O, metallic oxides, in general metallic oxides are basic in nature. In general, metallic oxides are basic in nature, and if you dissolve them in water, basic oxide will produce hydroxide. So I'll get sodium hydroxide, which is a base. So I can say this is basic oxide. While if I dissolve Cl2O7 in water, Cl2O7 in water is having +7 oxidation state. In Cl2O7, oxidation state of chlorine is +7. So it will give oxy acid in the same oxidation state. Means I'll get here SClO4. So it is giving acid here or oxy acid. So this is Cl2O7 is acidic oxide. That's how we can justify this point. Next is, okay, I think this chapter completed. Move to the next chapter, that is chemical bonding. Next chapter, chemical bonding. Which question? Al2O3 is amphoteric. Al2O3. Okay, someone is asking one question here. One question is, sir, in this question, how covalency is 6 there? Are coordination number concept knowing from coordination chemistry or not? Aluminium is central metal. In the surrounding of this, I have 1 monodentate ligand chlorine and 5 monodentate ligands water. That's how it becomes 6. Coordination number, simply you have to answer coordination number here. Okay, got it? How it is 6? Okay, Al2O3 is amphoteric. Okay, next is chemical bonding. Next topic is chemical bonding. Next topic is chemical bonding. Okay. Okay. Write the Lewis dot structure of CO molecule. So to write the Lewis dot structure of any molecule, I'll tell you the very easy method. Okay. Al2O3 amphoteric. Al2O3 amphoteric. Okay. ठीक है, चलो. Now question is Lewis dot structure of carbon monoxide. So knowing in carbon monoxide we have this kind of bonding. Carbon, oxygen is present. Carbon is having 4 electrons in the valence shell and oxygen is having 6 electrons in the valence shell. So if I make double bond here, octet of oxygen get completed. Now it become 8 electrons and carbon is becoming 6 electrons in the valence shell now. So now octet of oxygen get completed but carbon not completed. So what will happen there? Oxygen will donate its lone pair to the carbon. So now octet of carbon will also get completed and it is having now 8 electrons. That's how bonding takes place here. So whenever they're asking Lewis dot structure for any molecule, firstly think about the structure of molecule itself in terms of the covalent, or if coordinate present then coordinate also. So now in case of carbon monoxide, what I said here, it is one coordinate bond like this and 2 covalent bonds. Now they're asking question about the Lewis dot structure. So easier method is convert coordinate bond into covalent bond if it is present there. So here I have one coordinate bond. So I will convert coordinate into covalent. How will convert? You're knowing this is these two double bonds I'm writing as it is. I'm converting now coordinate bond into covalent bond. So easier method is draw single bond, plus charge on donor, minus charge on acceptor. Here, who is the donor? Oxygen. So I'll keep plus charge on oxygen. Who is acceptor? Carbon. So I'll keep minus charge on carbon. After that, just put the electrons of valence shell. For example, here, it is a carbon. Carbon is having how many electrons in the valence shell? 4. Carbon atom. Carbon atom is having 4 electrons in the valence shell. And now it is a minus charge, so 5. Minus means taking 1 electron. So out of 5 electrons of carbon minus, 3 are shared with the oxygen and 2 are non-bonded. Likewise, oxygen also. Oxygen atom is having 6 electrons in the valence shell. Oxygen atom is having 6 electrons in the valence shell. And now it is plus charge, means out of 6, 1 gone. How many left behind? 5. So here I will put 3 dots which are shared, or 3 electrons which are shared with the carbon, and 2 are non-bonded. Now ignore these bonds, there will be the Lewis dot structure. So here I can simply write Lewis dot structure something like this. Carbon, 3 electrons, oxygen, 3 electrons, they are shared, 3 electrons, 2 electrons of carbon and 2 electrons of this oxygen are not shared. Is it clear now? So this is the Lewis dot structure of carbon monoxide. Okay, got the concept how to write the Lewis dot structure? Don't waste your time on thinking about the electron and everything. Just go for the actual structure. If coordinate present, convert into covalent, and accordingly we have to place the electrons only. Later on, ignore the bond. Remaining structure is Lewis dot structure. Okay or not? This is the easier method to find. For example, so you can observe here. This is the Lewis dot structure written here for the carbon monoxide. Next question is write the Lewis dot structure of nitrite and NO2 minus. So same point I will say here also, go for the actual structure and then put the dots there. NO2 minus. How many electrons in the valence shell of nitrogen atom? 5. NO2 minus given, so O is making 1 double bond and O minus is making 1 single bond. Out of 5 electrons, now there is no coordinate bond here, so we can directly go for the dots here. Nitrogen, how many electrons in the valence shell? Nitrogen atom, 5 electrons in the valence shell. Out of 5, 2 are shared with this oxygen and 1 with this oxygen. Am I right or not? So how many non-bonded? 3. Oxygen atom, 6 electrons in the valence shell, 2 are shared and remaining 4 are not bonded. Oxygen minus 1. Oxygen minus 1. Oxygen minus 1 means 7 electrons. Oxygen 6 minus 1 7. So O minus is having 7 electrons in the valence shell. Out of 7, 1 is shared, and so shared I will represent here. It is single bond, so I can represent like this. So one coming from nitrogen, one coming from O minus. Out of 7 electrons of O minus, one is shared. So how many non-bonded? 6. 1, 2, 3, 4, 5, 6. Now ignore these bonds. Remaining thing is Lewis dot structure. Okay or not? Yeah, resonance will happen, so we can go for opposite structure also. Okay. So if I consider resonance, I can write just another structure also for this one. Okay, so we can have 2 Lewis dot structures here. Next question. Okay, now, okay, one important point, when you are solving the bond parameters, I said one concept, key we can find van der Waals radius for noble gases as well as other elements also. For example, if you want to find van der Waals radius of chlorine atom, then you will take Cl2 molecule. What you will take? Cl2 molecule. Van der Waals radius we can find for the noble gases as well as other elements also. For example, if I want to find the van der Waals radius of chlorine atom, then I will go for Cl2 molecule. But I'll go for Cl2 molecule. So here one Cl2 molecule means 2 chlorine atoms bonded like this. 2 chlorine atoms. This is Cl2 molecule. Now in this case, half of this bond length will be covalent. Half of this is going to be covalent radius, and half of this chlorine, they are not bonded now. This chlorine and this chlorine, they are not bonded. So half of this distance is going to be van der Waals radius. Got the concept or not? So we can find van der Waals radius of chlorine atom by taking Cl2 solid. In Cl2 solid, select 2 chlorine atoms which are not bonded, like this chlorine, and this one. They are not bonded. I'll select half of them as the van der Waals radius. Okay, this is the way to find the radius, van der Waals radius for chlorine atom. By this, what I am saying here, we can find van der Waals radius for noble gases as well as for other elements. Okay. Now, bond angle. Bond angle, you are knowing it is the angle between 2 bonds attached to the same atom. That is what bond angle. Okay, now how we can find? Answer is by X-ray diffraction, electron diffraction, or spectroscopic techniques. Okay, bond length concept is very easy. In general, top to bottom, you are knowing, as we are moving top to bottom, size increases, bond length increases. In case of same kind of elements, for example, carbon-carbon bond, so carbon-carbon single bond, carbon-carbon single bond, carbon-carbon double bond, carbon-carbon triple bond. Obviously, single bond is having more bond length than the triple bond. Logic is very simple. In this case, single bonds effective overlapping is very less. But always remember, if you have very small atom like hydrogen, so let's say I'm comparing HH single bond with the C triple bond C. HH, hydrogen is the smallest atom of periodic table. So here 2 very small atoms are bonded, and here 2 large atoms are bonded as compared to the hydrogen. So in this case, irrespective of the bond order, we can simply answer here, small size hydrogen is present there. That's why bond length of HH is less than the C triple bond C. Okay or not? One more important fact, let's say you are comparing carbon-carbon single bond versus carbon-nitrogen single bond. Now in a period, size has less importance. In a period, size has less importance to determine the properties. So let's say I'm observing carbon-carbon single bond versus carbon-nitrogen single bond. Carbon size factor I can ignore. Go for the bond order, same single bond. So here what is important factor? Delta En. In case of Cn bond, N is delta minus and C is delta plus. Here it is no, En difference is 0. So here plus minus charge present, which will create attraction between them, and that's why they will come closer. And this Cn single bond is having less bond length than the Cc single bond. With the same logic, I can explain C triple bond C versus C triple bond N. In C, carbon, nitrogen and carbon or nitrogen, they belong to same period, and in a period size has less importance. So go for delta En in this case. Delta En for Cn is present, so plus minus charge, and Cc not having any En value. En difference is 0 here. So now in this case, plus minus will, same logic, plus minus attraction, bond length is going to be less. So Cc single bond is longer than Cn single bond. Cc triple bond is longer than Cn triple bond. Here, if I compare C double bond C with the C double bond N, as per the logic, obviously Cn double bond must be less than the Cc double bond. But if you check the NCERT data for C double bond N, they are writing 138 picometer. For C double bond C, they are saying 133 picometer. Means as per the NCERT data, CC double bond is less than the CN double bond. Technically, logically, it is not correct, but NCERT is writing, so there is no choice, we have to follow it. While other cases they are explaining correctly and they are writing correctly also, like CC single bond versus CN single bond, delta En present, attraction is there, length is less. Here also same logic. So CC single bond, you can check data here, it is more than CN single bond. Only for double bond part, CN versus CC, they are not writing correctly. Okay or not? For bond length, strictly for bond length. In bond energy, we have to follow the correct concept because they are writing correct data there. Only for bond length, CC double bond versus CN double bond, we have to go according to the NCERT. Only for bond length. Only for bond length, CC versus CN. Is it clear or not? Okay, got it. Next point. Let's say they are asking bond length, HH bond length given, CH bond length given, and CC single bond given. So here HH means two small atoms, CH means one large and one small atom, and here two large atoms. So obviously this is going to be smallest length and is going to be the maximum length among these three. Is it clear or not? In this way also we can find the bond length concept here. Whenever H is present, just keep things in mind. It is smallest atom of the periodic table, which make it very small bond length also. Okay. Next concept. Now, bond energy definition is very important. Bond energy is the energy required to break 1 mole of bond of particular type. 1 mole of bond of particular type into the isolated gaseous atoms. What is the important point here? We have to break 1 mole of bond of particular type. You can read here, it is defined as the amount of energy required to break 1 mole of bonds of a particular type. Particular type means 1 mole of single bond, 1 mole of double bond, or 1 mole of triple bond. So what is the important concept here? For the bond energy, we have to break 1 mole of bond of particular type. Particular type means 1 mole of single bond, or 1 mole of double bond, or 1 mole of triple bond. And one example given here, you can read in NCERT. Here they are breaking H2. So in this case, they are breaking actually 1 mole of single bond. You are knowing in case of H2 is hydrogen single bond. So actually we are breaking single bond. If it is O2, it is double bond, so we are breaking here 1 mole of double bond, and for N2 we are breaking 1 mole of triple bond. So concept is, for the bond energy you have to break 1 mole of bond of particular type, 1 mole of bond of particular type into the isolated gaseous atoms. Okay or not? And always remember, whenever you are defining bond enthalpy, you have to take given molecule in gas phase, and obviously you are making isolated gas atom, means overall things must be in gas phase. For example, if you want to define bond enthalpy of water, you knowing water is at room temperature, water is liquid. But when you are defining the bond enthalpy, what to take there? H2O gas. What to take there? H2O gas. One more important point is here. Let's say you are observing bond enthalpy of water, H2O. H2O given. Now in case of H2O molecule, left bond and right bond, both are identical, both have same bond enthalpies. But if you are breaking in sequential manner, means one after another, for example, you are breaking this bond, then breaking next bond, they are not going to be same. Well, sir, why not same? Because if you are breaking this first bond, now what left there? HO. Now breaking this bond of HO. So difference is, first I am breaking bond from H2O, next I am breaking bond from HO. So how they can be same? So point is very simple. In case of H2O molecule, if they're asking if the both bonds are identical, yes. Are they having same bond enthalpies? Yes. Are they having same successive bond enthalpies? No. Successive bond enthalpy means I am breaking one bond after another bond. For example, here, if I am breaking first bond, it is having energy bond enthalpy different than the next bond breaking. Is it clear or not? So that's what you can check here also for H2O. When I am breaking first bond, energy. Now, what I am breaking here? I am breaking 1 mole of H2O gas taken. So I am writing here HOH taken. I am breaking this bond, let's say. So now what I'll get here? HO gas and H gas. H gas and OH gas. Value is here 502. Don't memorize it. Just observe the data. Then I'm breaking next bond. So next time I'll break from the OH. So if I'm breaking OH, I'll get over H and O. This time value is what? 427. Means if I'm observing the Successive bond enthalpy, they are not going to be same. So average value I can take here. So 502, 427 divided by the 2. So what is the important concept here? I am defining bond enthalpy, so I have to take H2 and OH in gas phase, or anything whatever is taken for the bond enthalpy purpose, you have to take in gas phase. Is it clear or not? Logic is clear to you or not? Okay, this is very important observation based on the NCERT. Now, few important cases of the bond enthalpy and bond length. For example, ozone molecule given. In case of ozone molecule, this is the resonance structure of ozone. Sir, why are you saying resonance structure? Here in this structure I have drawn, in this structure of ozone I have drawn oxygen double bond and coordinate bond like this. But we can write opposite also now. We can write coordinate bond here and double bond this side. So we have two RS for the ozone and both are equivalent RS. So in case of ozone molecule, all oxygen bond lengths are going to be equal, because if I combine these two structures, means these two RS, I can get resonance hybrid like this OO, and partial bond will come here, and that's how this bond length oxygen bond length become equal. And that's what NCERT is explaining. Oxygen single bond length is 148 and oxygen double bond length is 121. But in case of ozone molecule, when I'm going for the actual structure, there is RS only. What I'm observing, both bond lengths are between 148 and 121. It is 128 and 128. Both are exactly equal. Why? Because of the equivalent resonance. So whenever you are writing double bonded and single bonded structure of the ozone, they are only RS. They are not the actual structure. Actual structure is this, and which is having equal bond lengths. So in the bond order we can find total bonds are 1, 2, 3. 3 bonds are distributed between two places. So 3 by 2 means each bond order is 1.5. Chalo, next question. Question is there, explain the structure of CO3 2- ion in terms of the resonance. So CO3 2-, I will write a structure here, CO3 2-, C double bond O, O-. If I am writing this structure, I am observing here, it is minus single double, means here O-, minus charge present on oxygen can go for the resonance. So for example, this is getting delocalized in this manner. So I will write next structure here, C, O-, double bond O, O-. Likewise, I can think about the delocalization of this minus also, and by this delocalization, I will get next structure here. I will write, okay, I write here C. This is going to become O-, here double bond O and O-. So how many RS coming for the CO3 2-? You can clearly observe it is having how many RS? 3 RS. 3 RS, or we can say 3 Lewis dot structures. Is it clear or not? What is the important fact here? You can observe all these 3 RS are identical. For example, in first RS, these two oxygens are minus, this oxygen is 0 charge. These two oxygens are minus, this is 0 charge. These two oxygens are minus, this is 0 charge. Means all 3 RS are identical. All 3 RS are identical. It means all the carbon oxygen bond lengths, because all 3 CO bond lengths are going for the resonance, all CO bond lengths are going to be equal. So if I write the resonance hybrid of the carbonate ion, I can write like this, CO, O, and O. Now you can observe here total number of bonds in, let's say consider this first RS. Total number of bonds between CO 1, 2, 3, 4. 4 bonds. 1, 2, 3, 4 bonds. 4 bonds are distributed equally between 3 places. Sir, why equally distributed? Because they are equivalent RS. Because they are equivalent RS. So I can say equally distributed. So each bond is going to be 4 by 3. I'm repeating again. Total number of bonds in the RS 1, 2, 3, 4 for the CO part. So 3 bonds, 1, 2, 3, 4 bonds are there, and they're distributed in 3 places. So each bond order is going to be 4 by 3 means equal to 1.33. Second part is the charge distribution. Charge is here -1, -1, -2 charge, and -2 charge is equally distributed on 1, 2, 3 oxygen atoms. So each will get 2 by 3, -2 by 3, -2 by 3, and -2 by 3. This is the real structure of carbonate ion. So here they can ask many questions, like if they're asking number of RS and bond parameter, everything. So if they're asking which of the following is correct structure of carbonate ion, let's say first option is given this one and second option is given this one. What to take? Answer quickly. Correct structure of carbonate ion. This is given option number 1. This is given option number 2. What to correct? What to tick there? Which one is correct answer? Answer quickly. Correct structure of carbonate ion. Correct structure of carbonate, and what to answer? RS or RH? Obviously RH. RH is the real structure. RS are the hypothetical structures what we are writing to explain the properties. I think this part is also clear to you. Okay. Next is the very important question. Explain the structure of carbon dioxide molecule. So now in case of carbonate bond or is coming 1.33, it means carbon oxygen bond length is going to be between carbon oxygen single bond and carbon oxygen double bond. Now come to the next question, structure of carbon dioxide. Now in case of carbon dioxide, you can observe here carbon dioxide, oxygen double bond, carbon double bond, oxygen. You can observe here oxygen is containing non-bonded pair of electron. This oxygen also containing non-bonded pair of electrons. So now observe, for this non-bonded pair of electron, this pi is alternate. So we can go for resonance like this. Based on this resonance, I can write a structure here. This O is making bond here, so it become O triple bond plus, and this is single bond O minus. Now, in similar manner, we can think about the opposite direction also, like this lone pair and this pi electron can be delocalized, and based on this, I can write next RS here. So, in case of first of all, in carbon dioxide molecule, if they are asking resonance is present or not, answer is yes, it is present. How it is present? Let's observe again. In this case, for this lone pair, next pi is alternate. For the second lone pair, this pi is alternate. So, I can write one more RS here by the delocalization of this. Delocalize in this manner, this become O minus, single bond C triple bond O plus. So first question here, in case of carbon dioxide molecule, resonance is present or not? Resonance is present or not? Yes or no? Yes, it is present. Second question, how many RS are possible? Answer is 3 RS are there. Is it clear or not? Next, and the most important concept, due to the resonance effect in carbon dioxide, carbon oxygen bond length is coming between carbon oxygen double bond and triple bond. Coming between carbon oxygen double bond and carbon oxygen triple bond. So they can ask, in carbon dioxide molecule, carbon oxygen bond length is, answer is in between carbon oxygen double bond and carbon oxygen triple bond. Sir, why? Because of the resonance. Is it clear or not? So I'm writing, I'm just telling you a few questions. Just quickly answer them. First question, in carbon dioxide molecule, resonance is present or not? Yes or no? Resonance is present or not? Yes or no? Yes or no? Yes, very good. Now, how many RS or how many Lewis dot structures are present? 1, 2, 3, 4. How many Lewis dot structures are present for carbon dioxide? Number of RS or number of Lewis dot structures? They can ask in this manner. Number of RS or number of Lewis dot structures? 3 are present. Next question. Carbon oxygen bond length of carbon dioxide is, first option, equal to the normal carbon oxygen double bond. Second option, between carbon oxygen double bond and triple bond. Carbon oxygen bond length in carbon dioxide molecule is, first option, equal to normal carbon oxygen double bond, and second question, between carbon oxygen double bond and triple bond. Answer quickly. Between carbon oxygen triple bond. Very good. So these are the 3 important questions for the carbon dioxide. Same way they can ask for carbonate, and also that is discussed earlier. Okay, move to the next question. Polarity of the bond. Polarity of bond means dipole moment. Formula of dipole moment is known to be mu is equal to, formula of dipole moment is known to be mu is equal to Q into D. It is a vector quantity. It is a vector quantity, and dipole moment of a chemical bond is represented by this arrow and this cross. This is the vector representation for the dipole moment of a bond or of a molecule. So whenever you are representing dipole moment of a molecule for a bond or for a lone pair, we have to use this arrow. This is the vector representation for the dipole moment in a molecule. For example, if you want to represent the dipole moment of HF, you want to represent the dipole moment of HF. Fluorine is delta minus and H is delta plus. So we have to draw a vector like this from H to F, from delta plus to delta minus with the cross. Is it clear or not? Okay. Now dipole moment is a vector quantity, so obviously it depends on vector addition also. So whenever you have molecules like A2, any A2 molecule means a diatomic molecule. Homoatomic molecule is having 0 dipole moment. Whenever it is a homodiatomic molecule, dipole moment is 0. Whenever you have molecule like CH4, BCl3, BCl2, PCl5, SF6, IF7 like this. What is common in all these cases? Actually, you have molecule ABN, where N value is more than equal to 2 and A is not carrying lone pair. ABN type of molecule where N value is more than equal to 2 and A is not carrying lone pair, here dipole moment is going to be 0. Is it clear or not? Like for example, if I'm writing BCl3 structure, BCl3 structure, this vector dipole, this vector and this vector, they are cancelled. You're knowing if you are keeping 3 vectors of equal magnitude at angle 120 degree, net vector sum is going to be 0. Okay or not? So these are the two important cases. One point I said A2 dipole moment 0. Second ABN where N value is more than equal to 2 and A is not carrying lone pair, dipole moment is going to be 0. Other cases we have to find by writing the structure. Is it clear or not? Now come to the most important case, dipole moment of NH3 versus NF3. Most important case, dipole moment of NH3 versus NF3. You can observe here, in case of NH3 molecule, out of N and H, who is more electronegative? So obviously N. So direction of dipole moment is towards N, towards N, towards N. So direction of dipole moment towards N, and towards N, because out of N and H, dipole moment of En of N is more than H. For the lone pairs, we have to keep dipole moment away from the atom. So in case of NH3, all vectors are going in same direction, so net vector sum is going to be more. While in case of NF3, you can observe out of N and F, dipole En of fluorine is more. So direction of dipole moment is towards fluorine, and towards fluorine. While for the lone pair, we have to represent away from the atom, so it's away from nitrogen. So you can observe here, these 3 NF bond dipole moments are opposite to the lone pair dipole moment, and that's why they are cancelling each other, and overall vector addition is going to be less. Got the concept now? So out of NH3, NF3, dipole moment of NF3 is less and is very small. NF3 dipole moment is very small. For example, you can check the data also. NF3 dipole moment is 0.23. NF3 dipole moment is 0.23. It is very less. You can check other dipole, obviously more than 0. Obviously 0 is the minimum possible dipole moment. Okay, 0 is the minimum possible dipole moment. So among non-zero cases, NF3 is very less. I'm not saying minimum, I'm saying very less. So dipole moment of NF3 you can observe is 0.23 only. Very little value is coming. Is it clear or not? You can check other data, non-zero data. HF 1.78, these are given here. 0.23 is very less value in this table. Is it clear or not? So other than 0 cases, NF3 is very small dipole moment. Is it clear or not? Obviously 0 is the minimum possible value of dipole moment. Whenever dipole moment is a non-zero, we are saying the permanent dipole moment is present. And whenever it is 0, we are saying permanent dipole moment is not present. Okay or not? Okay, among HF to HI, as we move from HF to HI, delta En decreases, charge decreases. So dipole moment also decreases. You can observe HF to HI dipole moment is decreasing. One more point you can observe based on the NCERT table only, that dipole moment of H2O is more than the dipole moment of HF. Dipole moment of H2O is more than the dipole moment of HF. Is it clear or not? Next is okay. Okay. Here I will discuss few important cases related to the lone pair. For example, SO2 is given. In case of SO2 molecule, it is sulfur, double bond oxygen and lone pair. It is sp2 hybridized, one lone pair present, so it become bent geometry. Other side I'm taking H2 molecule, or better take NH3 molecule, NH3 molecule, sp3 hybridized, trigonal pyramidal geometry. Now come to the bond angle, the most important discussion here. sp2 hybridization means parental angle is 120. Obviously, because of lone pair, angle is going to be less than 120. Parental angle means expected angle from the sp2 is 120. But due to lone pair repulsion, angle is going to become less than 120. In this case of sp3, parental angle 109 degrees, and due to the repulsion is going to be less than 109 degree. But what is important point? Observe the bond angle for ammonia written here 107 degree, and for SO2 written there 119.5 degrees. So what I am observing here, in case of SO2, because of this lone pair bond pair repulsion, and obviously bond pair also repelling here, angle is decreasing only 0.5 here. 120 minus 0.5 is equal to 119.5, decreasing only 0.5. In this case, lone pair repelling to the bonds, and bonds are also repelling. Due to overall effect, here angle is decreasing 2 degree. Like sp3 means expected angle 109 and actual value 107, means decreasing only 2 degrees in air. Here decreasing 2 degrees and here decreasing only 0.5 degree. So point is, sir, why in this case decrease is less? Because here is double bonds. Double bond present, so the bond pair repulsion is also significantly high. Obviously less than the lone pair bond pair repulsion. Lone pair bond pair repulsion is more than bond pair repulsion. I'm not denying this. What I'm saying here, bond pair repulsion is significantly high, not higher than the LPBP. And that's why here bond angle is not decreasing much. Decreasing because LPBP more than BPBP, but not decreasing much. Because double bonds are there, so they will repel more as compared to single bond cases. Okay, and here decrease is going to be less. While in case of ammonia, it is single bond, so bond pair repulsion is very less, so overall decrease is more. Got the concept or not? So they can ask one question here. In case of SO2 molecule, bond angle is decreasing only 0.5 from the expected angle based on the hybrid orbitals, while in case of ammonia, it is decreasing 2 degrees. Logic. In case of SO2 molecule, it is a double bond. And double bond repulsion is more than the single bond repulsion. There's an overall decrease. In case of ammonia is more, and for SO2 it is less decrease. Okay or not? This is one important observation here. Next important part, if you are going for the SF4 molecule given, here you are knowing hybridization is going to be sp3d. Hybridization is going to be sp3d. sp3d means parental geometry trigonal bipyramidal. Now in this case I have to keep one lone pair. So they can ask question, what is the correct structure of SF4 and how many possibilities are there for the SF4? So one possibility, I can keep lone pair at equatorial, so other places are going to be. Another possibility, I can keep lone pair at axial, so other places I have to place fluorine there. Okay now. So now two questions are possible. One question is, what is the correct structure of SF4? So obviously first is, this is the correct structure, which is named as a seesaw geometry or distorted tetrahedron or folded square. Another question is, how many structures can be drawn for the SF4 molecule? Answer, we can draw two structures there. One case where lone pair is placed at equatorial, and second case where lone pair is placed at axial. Another question is, they can give these two structures and ask the stability. So obviously this is the correct structure, means this is more stable structure than the second one. Is it clear or not? Likewise for ClF3 also they can ask question. In case of ClF3 molecule, it is having sp3d hybridization 3 sigma 2 lone pairs. So first question is, how many structures we can draw here? So it is also trigonal bipyramidal. Now we have one possibility is, both the lone pairs are placed at equatorial. Both the lone pairs are placed at equatorial. One possibility. Next possibility is, one lone pair is placed at equatorial and one at axial. One at equatorial and one at axial. And next possibility is, both the lone pairs are placed at axial, so other sides, means equatorial sides, are occupied by fluorine. So how many structures can be drawn for the ClF3 molecule? How many structures can be drawn for ClF3 molecule? 3 structures. both lone pairs at equatorial, both lone pairs at axial, and one at axial, one at equatorial. And out of these three, the correct structure is obviously first one, or most suitable structure is first one, when I'm keeping both the lone pairs at equatorial. This is a T-shaped structure. Is it clear? Understood or not? Okay, these are two important points here for the structure part. Okay, overlapping concept, you're knowing overlapping can be positive, negative, or zero. Positive overlapping means same sign combining, like here you can observe plus 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 plus, or minus minus, here minus 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 minus. So combination of plus plus or minus minus waves is positive overlapping. Combination of opposite like plus minus minus plus is negative overlapping. And the cases where they are having different orientation or different approach like this is known as zero overlap. Here it is px and s combining like this, not possible. Here it is one is px and another is py. Px, py, they have different orientation, they cannot combine. So we have three kind of overlappings here as per this concept: positive, negative, and zero. Positive means in phase, negative means out of phase. Zero is out of phase due to different orientation or different directions of approach. Okay, next is hybridization. You know it is taking place to minimize the repulsion. N atomic orbitals are intermixing to make n hybrid orbitals. For example, if you have two atomic orbitals, they will form two hybrid orbitals. If you have three atomic orbitals, they will form three hybrid orbitals. So for example, I want to make sp2, then I need one s orbital and two p orbitals. So one s orbital and two p orbitals, they will intermix. Total three orbitals are there, one s and two p orbitals. Total three atomic orbitals, they will give three hybrid orbitals, will be named as sp2. So three sp2 hybrid orbitals will form, kept at the angle 120 degrees. Next is, this table is very important. You are knowing if hybridization is a dsp2, geometry is going to be a square planar. In dsp2, this d is going to be n minus 1 dx square minus y square. S is ns and np are npx plus npy. Is it clear or not? So dsp2 is a square planar. Trigonal biplanar geometry obtained for sp3d, or if I go for the coordination compounds or D block, then I can have dsp3 also. So in P block sp3d only, but or in case of D block, if I include D block also, or if I consider coordination chemistry, then trigonal biplanar possible for sp3d or for dsp3 also. Next is square pyramidal. Square pyramidal is coming from the octal. Okay, I'll go for this first. sp3d2 is there. If sp3 is there, then I can have many geometries like octahedral for the all bond pair cases. Then we can have a square pyramidal also. For example, if hybridization is sp3d2, then I can have octahedral geometry. And now in this octahedral, in two places, if I keep lone pair, it is going to be square planar also. Is it clear or not? Square pyramidal is also possible there, like in octahedral. In octahedral, if I keep one lone pair and one bond, like in octahedral part, if one lone pair is taken here, one lone pair is taken here, like this, it is going to be the square pyramidal geometry also. Is it clear or not? So here it is a square pyramidal geometry, you can clearly observe here. Got the concept now? So what concept I'm making, in case of sp3d2, we can have octahedral, we can have octahedral geometry, we can have a square planar geometry, or we can have a square pyramidal geometry, depending on the cases. For example, no lone pair, all 6 bonds are sigma, then it is octahedral. 2 lone pairs is square pyramidal, is square planar, and 1 lone pair will make it a square pyramidal. This is for the sp3d2. Okay or not? Octahedral, sp3d2 or d2 sp3, they are saying considering coordination chemistry. If it is coordination chemistry, then I can have d2 sp3 also for the octahedral. Okay. Next is molecular orbital theory. As per the molecular orbital theory, if n atomic orbitals, first of all, molecular orbital theory is based on LCAO. Molecular orbital theory is based on LCO. LCO means linear combination of atomic orbitals. Molecular orbital theory is based on LCAO, linear combination of atomic orbitals, and it is an approximate method. It is an approximate method. Is it clear or not? As per molecular orbital theory, if n atomic, for example, 2 atomic orbitals are going for the linear combination, or simply we can say combination also, will produce 2 molecular orbitals. Out of 2, one is going to be bonding molecular orbital and one is going to be anti-bonding molecular orbital. Is it clear or not? So I can generalize also. Let's say we have n atomic orbitals. I will get n molecular orbitals by the combination. Out of n molecular orbitals, n by 2 are going to be bonding molecular orbitals and n by 2 are going to be anti-bonding molecular orbitals. Is it clear or not? Energy sequence is very important for here for the molecular orbital theory. And in case of molecular orbital theory, if you're writing electronic configuration, for O2, F2 and other or ions related to them, then configuration is going to be sigma 1s, sigma energy order is sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, then sigma 2pz, pi 2px, pi 2py, pi star 2px, pi star 2py and sigma star 2pz. Is it clear or not? Now if it is Be2, Li2, Be2, B2, C2 and N2, B2, C2 and N2. In these cases, the sigma 2pz is having energy more than pi 2px and pi 2py due to the 2s2p mixing. So in case of Li2, Be2, B2, C2, N2, in these cases 2s2p mixing is present and that's why energy order is sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, and energy of sigma 2pz is going to be more than pi 2px and pi 2py. So here I will get a value pi 2px, pi 2py, then sigma 2pz, then obviously pi star 2px, pi star 2py and sigma star 2pz. And based on this energy sequence, we can fill electrons there. For example, let's say someone is asking for the C2 molecule. C2 molecules, I have how many electrons? 12 electrons. C2 is vapor, obviously. So C2, 12 electrons are there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 0, 0, 0, 0. This is the configuration for the C2 molecule. Based on this, we can find bond order also. Bond order is number of bonding electrons minus anti-bonding divided by 2. So bonding electrons you can count 2 plus 2, 4, 4 plus 2, 6 plus 2, 8. 8 minus 4 by 2 is equal to 2. Means C2 we are having double bond. And both bonds are pi bonds. Both bonds are pi bonds. Sir, how will know that both are pi bonds? Very easy concept. Let's observe here. Sigma 1 has 2 electrons, sigma star 2 electron. So 2 minus 2, 0. Sigma 1 and sigma star 1 is cancel each other because electron count same. Sigma 2 has 2 electrons, sigma star 2 has 2 electron. So sigma 2 has 2 will cancel because they are having same number of electrons. Pi how many electrons? 2 plus 2, 4. And pi star is 0. Means no electron in anti-bonding of pi. So all 4 pi electrons will make bond. So you're knowing 2 electrons, 1 bond, 1 electron, half bond, 4 electrons, 2 bonds. And both are going to be pi bonds here. In this we can find. Likewise, you can think about the configuration of O2 also. O2, electron count 16. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. You can observe here, O2 is having unpaired electron in the pi star 2px and pi star 2py. That is why O2 is a paramagnetic. That's why O2 is a paramagnetic. Is it clear or not? So this is the energy order. One more point here, you can observe first shell is fully filled for the O2. So in the place of sigma 1s2 and sigma star 1s2, I can write here simply Kk. But I can write Kk. Kk means closed K shell. Similarly for C2 also you can observe, first shell is fully filled. Sigma 1s is 2 and sigma star 1s is also 2, fully filled. So here I can write simply Kk. Okay, this is a brief idea about the molecular orbital theory. Go for the direct method. If 14 electron count present for the diatomic, for diatomic like A2 type of molecule or AB type of molecule, diatomic molecule, 14 electrons present, bond order 3, going either side decrease by 0.5, like 15 electrons, bond order 2.5, 16 electrons, bond order 2. Likewise, you can go up to 20. For 20, bond order will come 0. Bond order 0 means molecule will not exist. Likewise, this side also go for 13, 2.5. 12 electrons, 2. You can go up to 10 here. Understood or not? In this, you can memorize bond order also. 14 electrons, bond order 3. Going any side, decrease by 0.5. Okay. So this chemical bonding is also completed. I am giving break of 10 minutes. Then we'll continue the next chapter. Okay. I am giving break of 10 minutes only. So now it is 8:55. So let's start at 95. Okay. Okay, so let's resume the class. Just confirm once. Audio, video, okay or not? Audio, video, is it okay? Okay. So 2 topics completed. Next is organic chemistry, some basic principles and techniques. Okay. First organic compound which was synthesized in lab, you're knowing it is urea. Problem number 8.1. How many sigma and pi bonds are present in the each of following molecule? How many sigma and pi bonds are present in the each of following molecules? You can observe the structure of molecule given there, and you have to find sigma and pi bonds. Okay. First molecule is given there. Observe here. HC triple bond C. Then CH. So next is CH double bond C. H and CH3. HCH3. And now you can easily count number of sigma bonds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Is it clear now? Pi bonds, triple bond presence here. We have 2 pi bonds, and double bond we have 1 pi bond. You can find nature of bond also, like it is CC single, CC sigma bond, or CS sigma bond, like that. You can find nature of bond by hybridization concept. For example, if they ask the nature of this sigma bonds, this carbon is sp hybridized and hydrogen will provide 1s orbital. So this sigma bond formed by sp 1s overlapping. Here this carbon is sp hybridized, so this sigma bond formed by sp overlapping. This carbon you can observe 3 sigma bonds, so it is sp2 hybridized. So we can say this sigma bond is formed by sp2 overlapping. This sigma bond is formed by sp2 overlapping. This carbon is sp2, this carbon also sp2. So this sigma bond formed by sp2 overlapping. This sigma bond formed by sp2 hydrogen provide 1s, so sp2 1s overlapping. Likewise, this carbon you can observe is sp3 hybridized, so this sigma bond formed by sp2 sp3 overlapping. This CH bonds, this carbon is sp3 and hydrogen provide 1s, so this sigma bond formed by sp3 1s overlapping. So not only number of sigma pi bond, they can ask nature of pi bond also, means what kind of overlapping is taking place there. Okay, next question is, what is the type of hybridization of each carbon of following compound? So first compound is given CH3Cl, so it is HCCl. So how many sigma bond? 3 sigma bonds around carbon and no lone pair. So hybridization is going to be sp3. Is it clear now? You are knowing that hybridization depends on lone pair and sigma count. Lone pair and sigma count. Based on that, we have to decide the hybridization. Okay, I'll like solve next molecule. See, it is given CH3 twice CO, means it is C double bond O CH3. So this carbon is going to be sp3, this carbon is going to be sp3, and this carbon is going to be sp2 hybridized. So in this way you can solve others also. Okay, move to the next question. It is very easy, so why to waste time here? Move to the next question. You know we have 3 type of bond formula. Complete formula, condensed formula, and bond line formula. Complete, condensed, and bond line. For example, if you are writing molecule with all the bonds present there, like this, you can observe here I am representing all the bonds here, CH, all the bonds are represented. It is complete formula. If I am writing only the condensed, like I am writing like this, let's say it is given, this molecule given, I am writing all the bonds, it is complete formula. Instead of writing this, if it is written like this, CH3, it is now condensed formula. Is it clear or not? And if I am using this bond line, it is known as line formula. In bond line formula, you can ignore carbon and you can ignore hydrogen attached to carbon. If any hydrogen is attached to the atom other than carbon, we have to represent in the bond line formula. For example, this molecule is given. Now in this case, if I want to write its bond line formula, I will write as it is one carbon, so I will write this as simply, okay, or let's say better take this example. This is taken, let's say CH3, CH2, CH2OH taken. Now I'm representing its bond line formula. So how many carbon atoms are there? 1, 2, 3. sp3 atoms you have to represent by zigzag method. And next is O. So here I will represent H also, because H is attached to the atom other than carbon. Okay, now if it is a triple bond situation, for example, let's say this compound is given, HC triple bond C CH2 OH. So now this is triple bond. Triple bond part is linear. So here I have to represent this thing linear. Triple bond, this triple bond represented here. This is carbon. Next carbon is what? CH2. This is CH2 carbon. Then this is next here. So carbon, this is carbon, this carbon. Then this next carbon. Then CH2. Next CH2 and then OH. Okay or not? So in case of bond line formula, if it is a triple bond part is going to be linear. sp hybridized, you are knowing. Okay now. In this way you can present the bond line formula. Come to the questions. Okay. Now they are asking few questions here, like expand each of following condensed formula into their complete structure formula. Complete structure formula means we have to represent each and every bond. That's all. So now it is given here, molecule given CH3, CH2, CO, CH2, CH3. So you can open the bonds. Like here, this carbon is having 3 bonds. I will write CH3 here. Likewise, I can represent all the bonds. It become complete structure formula. Next question is given. There are condensed formula given. Now we have to represent bond line formula. For bond line formula, what concept I said, if any hydrogen is attached to the carbon, you can ignore it. But if it is attached to the atom other than carbon, we have to represent it. For example, here it is OH present, so I have to represent it. NH2 present, we have to represent it. One more here, it is CN, so we have to represent CN complete. Is it clear? Understood the concept or not? We cannot represent just N, we have to represent CN there. Okay or not? Like now, these structures are there, bond line formula. Here you can observe for the triple bond part, they are not writing zigzag, they are writing linear manner, because triple bond is sp hybridized, atoms of a triple bond are sp hybridized, so we have to represent in linear manner. Triple bond part, sp3 part we can write zigzag, like I observe sp3, 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 sp, that is zigzag manner. But sp part, like triple bonded carbon, must be represented in linear manner in bond line formula. This is clear or not? Molecular model 3 are there, framework model, ball and stick model and space filling model. These are 3 framework models. Okay or not? Question. Chalo, theek hai. Okay. Question is, structure is given and we have to write the IUPAC name. Whenever you are writing IUPAC name, first of all, select the parent carbon chain. Select the parent carbon chain, then number it and finally name the compound. So now in this compound, you can observe there is no principal functional group. What is the rule for selection? Firstly, go for the maximum number of principal functional groups, maximum number of PFGs. After the number of PFGs, firstly go for the maximum number of principal functional groups. After that, go for the multiple bonds. After that, go for the longest chain, means number of carbons. And after that, go for the number of substituents. And if all these 4 conditions are not giving me the selection in proper way, then go for the alphabetical order. There is the last choice. Alphabetical order is last choice. So here, in this given compound, no parent principal functional group, no carbon-carbon multiple bond. Then go for the longest chain here. So this is the longest chain. Selection of parent carbon chain is done. Numbering, for the numbering rule is try to give lower number to the PFG, then try to give lower number to the multiple bond. Multiple bond means carbon-carbon multiple bond. It may be carbon-carbon double bond or carbon-carbon triple bond. After multiple bond, try to give lower number to the substituent. For the selection rule is try to have maximum number of PFG, then maximum number of multiple bond means carbon-carbon double bond or triple bond, then maximum number of carbons means longest chain, and then maximum number of the substituents. For numbering purpose, rule is try to give lower number to the PFG in the selected PCC, then lower number to the multiple bond, and then lower number to the substituent. And in any case, if it is symmetrical, go for the alphabetical order. Means alphabetical order is our last choice. Okay, so if I'm going from this side, it will be 1, 2. 2 coming from this side. This CS3, 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 all are substituent. From this side it is 1, 2, 3. So obviously this side is giving lower numbers 1, 2, 3, 4, 5, 6, 7, and 8. Accordingly, we can name it. Okay, so you can observe number 2 position, number 5 position, number 6 position are having Methyl groups, I can name it as a 2, 5, 6, a trimethyl, total 8 carbons are there, octane. Is it clear or not? Next example. Now this compound is given. What is the rule? Firstly, go for the selection of PCC. Video, audio not coming. Now is it coming? Yeah. Chalo, if it is coming, then no problem. We can continue. Okay, let's continue. Now, what is the rule? Firstly, select the parent carbon chain. So here, selection of PCC, firstly go for the PFG. So you can observe here OH is the principal functional group. So I will consider this carbon in the parent carbon chain. But here carbon present both sides, I can connect this entire thing, I can select as parent carbon chain. Then what is the rule? Give lower number to the PFG. From this side, PFG getting number 3. From this side, 1, 2, 3, 4, 5, 6. Getting number 6, and from this side getting number 3. So obviously give lower number to the PFG. So this is the selection. Okay or not? Now if OH is PFG, what is the suffix there? Ol. And CH3 is substituent, it is a methyl. So substituent named first I will write here 6 methyl, and then it is what? Total carbons 8, so oct, and single bond, so ane 3 ol. And you're knowing one concept, if after ane, ene or ine, if A, E, I, O, U, Y present, then this E is going to be cancelled. If you were saying for audio, now it is okay, done. Okay, understood or not? Next question. This molecule is given, rule is same, go for the selection of PCC first based on the PFG, followed by multiple bond, followed by carbon chain, followed by the substituents. Okay, so here carbonyl group given and both are ketones, so it means it is a PFG. So I will select this parent carbon chain. Sir, why? This carbon is related with the PFG. This carbon is related with the PFG, so I will include them, and this is my parent carbon chain. In this side is giving me lower number. Here ketone is PFG, so we have to use a suffix on. Okay, now accordingly we can name it hexane 2,5-dione. Is it clear or not? Next is, now this compound is given. Now in this compound, it is hexane 2,4-dione, 2 and 4, 2,4. Hexane 2,4-dione. Okay. Now this compound is given. Now in this case, the most important example, and by this I'll compare previous one also. Now here, carboxylic acid is coming first in the priority over this ketone. So now this carboxylic acid is a principal functional group. So this CO is going to be the substituent. In this CO, this double bonded oxygen is a substituent. And if double bonded oxygen is a substituent, we are using term oxo or keto. Is it clear or not? PFG is 1, 2, 3, 4, 5, 6. Now I will not use here own, because in this case this oxygen is substituent. Why is substituent? By carboxylic acid become PFG. So lower priority becomes substituent here. So I will name it as own. So 5 own hexane 1 carboxylic acid. So hexane hexane oic acid. E will be cancelled. Is it clear now? For COH, what is the rule? If carbon of carboxylic acid is the part of PCC, we have to use term oic acid, and not the part of PC, then carboxylic acid. Here, this carbon is the part of parent carbon chain, so I will write as oic acid, and this E is going to be cancelled or deleted. Is it clear or not? So what is the difference? In previous case, this CO as well as this CO, both are principal functional groups. So we have to use a suffix here. And suffix is going to be on. Is it clear or not? So name become hexane 2,4-dione. In this case, this CO is a substituent. Why is substituent? Because higher priority group present in carboxylic. So carboxylic acid become PFG. So this O becomes substituent, means oxo or keto term can be used here. Acid, so name will be hexane 5, sorry, prefix right before the word root. So 5-oxohexanoic acid. Is it clear or not? Got the concept? Next example, next question. Okay, so next is, okay, here compound is given and we have to write the name. Now in this case selection is very easy. This is the parent carbon chain. Now we have two possibilities. One, I can go right to left, left right. Let's say I'm going from left right, 1 2 3 4 5 and 6 like this. Now in this case there is no principal functional group, so go for the multiple bond. In this selection multiple bond is getting number 1, number 3 and number 5. So this selection is giving 1 3 5, while this selection is giving 1 3 and 5. Is it clear now? This selection is also giving same 1 3 and 5, means from both the sides multiple bond is getting same number 1 3 5 1 3 5. There is no substituent, means condition is symmetrical. Symmetrical condition means follow alphabetical order, and alphabetically ene is coming before ine. Is it clear now? Here I am following alphabetical order because condition is symmetrical, otherwise I will not go for this. Is it clear or not? So now in this case we can name it as, now it is total carbon count 6. Total carbon count is 6, so I can name it as hex. 1 and 3 position is ene and 5 position is ine. Alphabetically E will come first, so I'll write hex 1 comma 3 diene and 5 is ine. Now one more important concept. Whenever after the word root it is a di, tri, tetra, ene or ine. Okay, one question again, I'll discuss after that. So whenever after word root it is a diene, triene, tetraene or diine, triine, tetraene, just after the word root, then we have to put a there, so it become actually hexa. It become hexa. One question came, sir, if it is hexane 1, hexane 2 4 dione, this E will be dropped or not? No. In this case, just after this N, it is a D, not A, I, O, U, Y. It will not be dropped. Let's say it is this kind of name, hexane 2-one. So now just after the N, it is O. This E will be dropped. Okay or not? Understood? In this case, after N, it is not A, E, I, O, U, Y. What I said, after N, ene or ine, just after this, if it is A, E, I, O, U or Y, then this E is dropped. Then only this E is dropped. If it is other than this, will not be dropped. Okay or not? Okay, so this is important concept. Next one. Okay, these two compounds are given and we have to think about the IUPAC nomenclature. Okay, now for the multiple bonds, rule is whenever you are numbering multiple bond, they are getting continuous numbers, always getting continuous numbers except benzene. Okay, so in this case I have to give number like 1 2 2 3 3 4, like this numbers are allowed. 1 4 2 5, this kind of numbers are not allowed. Means multiple bond is always getting continuous numbers. Considering this point, I will number like this 1 2 3 4 5 6, or I can write like this also, opposite also, because it is symmetrical condition. Now let's say this example is given. This example is given. So now in this case, I will compare this example with another one. I'll take one more example here, this one, and I'll compare these two. Now in this structure, this NO2 is a substituent. You know, in few functions like NO2, halogen, ether, they're always a substituent. Okay, so now it is a substituent, and what is the priority? We have to go for, first we give lower number to the PFG, then multiple bond. It is not PFG, it is substituent only. So we have to go lower number to the multiple bond. Okay or not? Let's say I'm thinking in this manner: 1 2 3 4 5 6. So what will happen there? Multiple bond is getting number 1 and substituent getting number 6. Another possibility, if I'm going like this, 1, 2 and 3. So in this case, multiple bond getting same number 1, but now substituent is getting number 3, which is the lower than previous case. So this selection is correct. With this numbering correct, 1, 2, 3. Okay or not? I gave lower number to the multiple bond and I'm trying to give lower number to the substituent also, lower possible number there. But now in the second case, this OH is principal functional group. I'm giving 1 to this one and then I go this side 1, 2, 3. I'm giving continuous numbers to the multiple bond. So this is the numbering, and based on numbering you can easily write the names. You're knowing prefix and suffix, everything. You can easily go for the nomenclature. So now observe the difference here. In this case, NO2 is the substituent. So they're writing like this 1, 2, 3. Here OH is PFG, they're writing like this 1, 2, 3. OH is getting number 1 in this case because it is PFG. PFG related carbon. This carbon is getting number 1 because it is PFG related carbon. It does not mean that always PFG related carbon is number 1. No. Now someone is asking, sir, we cannot take, why we cannot take NO2 as one array or NO2? Is it PFG? Is it PFG? NO2, is it PFG? No, it is a substituent. And what is the concept here? Firstly, give lower number to the PFG, then lower number to the multiple bond, then lower number to the substituent. So I am giving lower number to the multiple bond first. I'll go like this. Are you getting or not? In this case, now it is a PFG, so I can give lower number to this carbon related to the principal functional group. Got the concept or not? Okay, this is the point. The next one. In case of benzene, if only one principal functional group is attached, then their common name can be used as IUPAC name. For example, I can name this as aminobenzene or aniline. Common name can be used as IUPAC name also. NO2 is present in the order. NO2 is a functional group, but not functional group. What I said, like I have to give lower number to the PFG, principal functional group. NO2 is a functional group, but not a principal functional group. Lower number to the PFG. Okay, NO2 is a functional group, but not a principal functional group. Cannot be principal functional group. Okay or not? Okay. So if one PFG attached to the benzene, then we can go for common naming as IUPAC name. We can consider common name as IUPAC name. Now they are saying few things here. Write the structural formula of orthoethyl anisole. So what is anisole? You are knowing. If I have taken this molecule PHOCH3, this is known as anisole. Now they are saying orthoethyl anisole means ortho position is having ethyl group, so C2H5 is attached there. Next question is given 2,3-dibromo 1-phenyl pentane. So firstly go for the condition here, pentane. So pentane 1, 2, 3, 4, 1, 2, 3, 4, 5 pentane. What they are saying here? 2,3-dibromo. So give numbers here. Let's say I'm giving like this 1, 2, 3, 4, 5. What they are saying that 2,3-dibromo. So number 2 position is bromine, number 3 position is bromine. 2,3-dibromo. What next they are saying? 1-phenyl. At one position attach phenyl group. So it become 2,3-dibromo 1-phenyl pentane. Is it clear or not? Next is given 4-ethyl 1-fluoro-nitrobenzene. Benzene. Firstly write the structure of benzene molecule. Then give numbers 1, 2, 3, 4, 5 and 6. What they are saying there? 4-methyl. Okay, attach ethyl. So ethyl group attached at number 4. 1-fluoro, attach fluorine here. 2-nitro, attach nitro at number 2. This is the structure of molecule. So this is way to write the structure of molecule based on the IUPAC nomenclature. Isomerism, let's go for the questions directly. If it is available, I think not available there. Okay, no problem. Using the curved arrow notation shows the formation of reactive intermediate when following covalent bonds undergo heterolytic cleavage. What is given? First molecule CH3, CH3, SCH3. Now sulfur is electronegative. Sulfur is electronegative. So if I'm going for heterolytic bond fission, I'll break this bond towards sulfur. So this becomes CH3 plus carbocation intermediate form, and this is going to become S minus CH3. Got the concept or not? Next is given there CH3CN. CH3CN. Here also CN is electronegative. If I'm representing heterolytic bond fission, I'll break like this. So this becomes CH3 plus and CN minus. Next is given there CH3 copper. CH3 copper. Now copper is metal, and metals have tendency to acquire positive charge. So here I will break this bond towards the CH3. Now I'll get CH3 minus carbon and intermediate, and copper is going to become plus. Is it clear or not? Next question. We have to identify them as electrophile or nucleophile for the. Okay, first is given HS minus, minus charge present, and lone pair also. This is nucleophile. BF3 electron deficient, electrophile, minus charge, nucleophile. Nitrogen contains lone pair, nucleophile. Plus charge, electrophile, plus charge, electrophile, minus charge, nucleophile, NO2 plus electrophile. Is it clear or not? So in this way you can easily find electrophile and nucleophile. In general, positively charged are electrophiles. In general, negatively charged are nucleophile. Electron deficient, electrophile. Lone pair donors, nucleophile. Few are acting as both electrophile as well as nucleophile. For example, carbonyl functional group. It is acting as electrophile as well as nucleophile. In this case, this carbon delta plus and oxygen delta minus present. This delta plus part will act as electrophile, and oxygen delta minus part will act as nucleophile. Is it clear or not? Okay, so very next question is given. Molecule given to you CH3CH double bond O, and you have to answer about this carbon. This carbon delta positive is going to act as electrophile. Likewise, next molecule given there CH3C triple bond N, and they're asking what the nature of this carbon atom. So this is delta plus and this is delta minus. This is going to act as electrophile. Okay or not? Now CH3I given, and here also this carbon is going to act as electrophile. Got the concept or not? Next is electronic effects. Now question is, which bond is more polar in the following pairs? First is given CH3H and CH3Br. So technically first is having CH bond, first is having CH bond, and next is having CBr bond. CH and CBr. Now you have to answer out of CH and CBr, which one is having more delta En? Which one is having more delta En? CN or CH or CBr? Obviously, delta En for CBr more. Got the concept or not? Next is given there CN and CO. So now answer. You have CN bond and you have CO bond. Where polarity more? Where delta En more? In this delta En more. Also polarity in the bond is more. More plus minus will develop in CO the CN. Next is given there CO versus CS. So obviously same answer here also. Out of carbon, oxygen, carbon, sulfur, who is having more delta En? So CO is having more delta En. More delta En, more polarity in the bond. You know, if En difference more polarity is going to develop in a given bond. Next is in which CC bond of this inductive expected to be least. So what concept you are knowing for the inductive? Let's say we have this kind of situation. This is given. Now Br will attract the electron density, so Br become delta minus, this carbon become delta plus. Next will attract, so it become less delta plus, represented as double delta plus. Now this will attract electron, now it become triple delta plus. Always remember, delta plus is bigger than double delta plus. Double delta plus bigger than triple delta plus. Means what we can say, as we increase the distance, inductive effect is drastically decreasing. As we are increasing the distance, inductive effect is drastically decreasing. So for which atom we have least inductive? Obviously the one who is far, means having maximum distance from the given halogen bromine in this case. Got the concept or not? So as you increase the distance, inductive effect is going to decrease drastically. Got the concept? Next one. Write the resonance structure of CH3CO minus, and so the movement of electron by the curved arrow. So now we have this molecule, this carbon and CH3C double bond O minus. this manner, and by the delocalization of this I can write next RsCH3C O minus double bond O. Both RS are identical, so this CO bond length and this CO bond length are going to be equal. You are knowing if equivalent resonance structures are present, then bond lengths which are going for the resonance are going to become equal. Is it clear or not? Next is given, write the resonance structure of the given molecule acrolein and find the relative stability order. Okay, so in case of acrolein molecule, this is the molecule that CH2 double bond CH double bond O. Let's say this is RS1. Assume this is RS1 or simply writing 1. One possibility I can delocalize like this. This double bond is going here and this pi bond breaking. So one RS I can write CH2 single bond CH double bond CH O minus and this is carbon plus. Let's say this is number 2. Another possibility I can delocalize pi bond in opposite direction. So I'll get this CH2 minus CH double bond CH O plus. Now what is the rule to find the stability of RS? First go for the octet. Complete octet is giving more stability than the incomplete octet. Once octet concept is same or identical or not giving answer, then go for the formal charge. More formal charge, compound is going to be less stable. More formal charge. After the formal charge, next concept is what? En and size is important in the case of groups. Important in the case of period and same atom. For example, sp carbon, sp2 carbon like that. And after that also, if you're not getting answer, then fourth point is what? Charge separation. After that, next point. Like charges are close, less stable. Unlike charges close, more stable. Okay. Now out of these four, first factor is what? Octet. In first case, octet is complete for all carbon and oxygen atoms. In this, hydrogen is not following octet rule. Hydrogen is following duplet rule. So I'm ignoring that one, obviously. So carbon, 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 oxygen, they are following octet rule. In next case, this is carbocation, 6 electron in the valence shell, not following octet rule or not having complete octet. Here oxygen is plus. So knowing oxygen atom is having how many electrons in the valence shell? Oxygen atom 6 electrons, plus charge, so 5 and one bond formed. So 6 electrons in the valence shell means number 2 and 3. They are not following octet rules or they are not having complete octet. So we can simply answer 1 is more stable than 2 and 3. So based on the octet, I got answer 1 is more than 2 and 3. But now come to the 2 and 3. Next factor is what? Formal charge. 1 plus charge, 1 minus charge. 1 plus charge, 1 minus charge. Formal charges are also same. Then this is also not giving answer. Next, what is the En and size? For En and size, compare same charges like plus plus or minus minus. Let's say I'm comparing minus minus. So minus on oxygen, minus on carbon means related with the same period. Same period means what to go for? En. Now it is number 2 structure. Minus on more En. You know oxygen is having more En than the carbon. So minus on more En, more stable. Minus on more En, more stable. So based on this, I can say out of 2, 3, who is more stable? 2 is more stable than 3. So this is the stability order of this. Now based on this, they can ask many other questions. For example, order of stability is done. They can ask for the order of potential energy. So knowing stability more, potential energy less. Next question, who will contribute more? So in case of non-equivalent RS, the most stable structure or least energy structure or RS will contribute maximum. So who will contribute maximum? 1. In this case, they can ask one more question. Who will not contribute? So least energy structure 3 is not going to contribute in this example. Okay or not? So this kind of question may be asked by the examiner. Come to the next part. Next problem is given. Explain why this is tert-butyl cation is more stable than ethyl carbon and CH3 plus is least stable cation. Very good question. In case of tert-butyl, we have 3 plus 3 plus 3, 9 alpha H, which are going for the hyperconjugation. Ethyl carbocation given. In case of ethyl carbocation, 3 alpha H are available, which are going for hyperconjugation. While in case of methyl carbocation, there is no alpha hydrogen to go for hyperconjugation. So based on this, we can simply answer tert-butyl carbocation is more stable than the ethyl carbocation, and ethyl is more stable than methyl carbocation. One very good question may be asked based on this problem also. Like in case of tert-butyl or in case of ethyl carbocation, why hyperconjugation is observed? So now go for the very simple concept here. This is sigma bond from sp3 of carbon and 1s of hydrogen. Means sp3 1s sp3 one sigma bond, and this is 2p of the carbocation. This 2p of sp3 one is they're almost parallel, so they can go for the hyperconjugation. Well, in this case, this CH bond, this 2p is perpendicular to these three CH bond, means plane of CH is perpendicular to the 2p orbital. Since they are perpendicular, so cannot go for hyperconjugation effect. So if they are asking in CH3 plus why hyperconjugation not present, you can answer here p orbital is perpendicular to the plane of CH bonds or CH bond. That's why not going for the hyperconjugation. While in this case, alpha CH orbital is parallel, almost parallel to the p orbital. That's why you can go for the hyperconjugation. That's what you can observe in the picture given in NCERT. Observe here. This sp3 1s sigma orbital is parallel to the 2p orbital of carbohydrate. That's why they can go for hyperconjugation. Is it clear or not? While in case of methyl, it is perpendicular, so not going for hyperconjugation. Next one, methods of purification. Many methods are there. Before that, one more concept, key, how to find the purity of compound. So purity of compound, what happened? 6. Okay, methods of purification. Before that, we can find the purity of compound by melting point, by boiling point, by melting point, by boiling point, or nowadays we can find by the chromatography and spectroscopic techniques. They are the latest technique to find the purity of compound. Okay, not. Sublimation is possible if out of 2 means impurity and organic compound is sublime and impurities are non-sublime. Crystallization is done by the condition if compound is having high solubility at high temperature and low solubility at room temperature. If it is not possible with the one solvent, take mixture of solvents. Distillation, simple distillation is performed when difference of boiling point is sufficiently high. Example, aniline and chloroform. Aniline and chloroform are separated by using the simple distillation technique. Next is fractional distillation. If boiling point difference is very less, then we can go for the fractional distillation. Fractional distillation is based on the fractionating column, where it is providing surface for the heat exchange between ascending vapors and descending condensed liquid, and some heat is going in opposite direction also from condensed liquid to the molecule who is getting vaporized. Okay, example, different fractions of crude oil, different, and the plate which is providing surface for the heat exchange is known as theoretical plate in fractional distillation. Now, what is the use here? So you are knowing key by the fractional distillation we can separate the different fractions of crude oil. Fractions of crude oil can be separated by the fractional distillation. Next is what? Distillation under reduced pressure. If organic compound is getting decomposed, at or below its boiling point or having very high boiling point, then we are going for the condition distillation under reduced pressure. For example, glycerol present glycerol in the soap industry present the spent lye is separated by this method, distillation under reduced pressure. Got the concept or not? So distillation under reduced pressure is applied if compound is getting decomposed, or required if a compound is getting decomposed at or below its boiling point, or compound itself is having high boiling point. Example is glycerol is separated from the spent lye in soap industry by this technique. Okay or not? Next, steam distillation. For steam distillation, as per our syllabus, we have 2 examples. One is aniline. Aniline is separated from aniline water mixture by this technique. Another is orthonitrophenol, para-nitrophenol present together. They can be separated by this technique because here orthonitrophenol is a steam volatile and immiscible in water. Here aniline is a steam volatile and immiscible in water. So steam distillation is valid if compound is a steam volatile but immiscible in water. Is it clear now? In this case, compound will boil below its boiling point, normal boiling point, because when sum of the pressure given by organic compound and given by water pressure are equal to the pressure of surrounding, then boiling point is achieved. Is it clear now? One very important concept here, directly go for this. Very important concept. If one of the substance in the mixture is water and the other a water substance, then mixture will boil close to but below 373 Kelvin. You are knowing normal boiling point of water is 373 Kelvin, and they are saying here ki if one substance is insoluble in water, then that it is close to 373 but slightly less, close to but below 373. Is it clear or not? Next is differential extraction. In differential extraction, condition is कि organic compound is more soluble in organic solvent than water. Is it clear or not? By this, in this technique, if compound is having very low solubility in the water, then go for the continuous extraction. If compound is less soluble in the organic solvent, if compound is less soluble in the organic compound, then go for the continuous extraction. You take large amount of the solvent in different parts, means small quantity of the large amount of solvent is taken. That is known as continuous extraction. Is it clear now? So repeatedly use the large amount of solvent in continuous extraction. This is required if compound is having low solubility in the organic solvent. Chromatography. Two types of chromatography are there: adsorption chromatography and partition chromatography. For partition chromatography, example is paper chromatography. In chromatography, this formula retardation factor is very important. It is the distance traveled by the substance from baseline divided by the distance traveled by solvent from the baseline. Means if compound is traveling more, its retardation factor is going to be more. Is it clear now? In case of column chromatography, we can take alumina or silica gel as stationary phase here. In case of paper chromatography, we have to take paper which is having water droplets trapped there acting as a stationary phase. Is it clear or not? Chromatography was name given on the basis of separation of colored compounds in the beginning, but now we can separate colorless compounds also. Okay. If spots of chromatography are not visible, then we can use some chemicals like iodine vapor can be used, or you can put the TLC plate inside the UV chamber. In case of amino acids, ninhydrin can be used. Next is detection of carbon. Okay, let's go for the questions directly. Okay. Condition is given there: on the combustion of 0.246 gram of an organic compound, it is giving 0.198 gram of carbon dioxide and 0.104 gram of water. Determine the percentage composition of carbon and hydrogen. So what is given there? Carbon dioxide is 0.198 grams. So moles of carbon dioxide is going to be 0. Divided by its molar mass, and it is a 44. Got the concept or not? So after that, I can find the moles of carbon. So you can observe one CO2 is having one carbon. So this many moles of CO2 is having same number of moles of carbon. So 0.198 by 44. This many moles of carbon present. Then weight of carbon is going to multiply by 12. Now I'm knowing the mass, weight of carbon divided by the total weight. Total weight is given 0.246 multiplied by 100. This is the percentage of carbon. Similarly, water is given here. H2O is given 0.104 gram. So moles of water is equal to, divided by its molar mass, it is 0.104 divided by the 18. Now come to the moles of hydrogen. So one H2O contains how many H? 2H. One H2O contains 2H. So 2H present here. So I can write here moles of hydrogen 0.104 divided by 18 multiplied by 2. This many moles of H present. Then mass of H. One H is having mass 1. So I can multiply with the 1. Molar mass is 1 for H. Is it clear now? Now I'm knowing mass of hydrogen divided by total mass. Total mass given 0.246 multiplied by 100. This is the percentage of hydrogen. Is it clear or not? So it is very easy. Just find the mass of H divided by total mass into 100, percentage of hydrogen. Likewise, find the mass of or weight of carbon divided by total multiplied by 100 is the percentage of carbon. Very easy question. Okay. Next is question is given here. In Dumas method for the estimation of nitrogen, 0.3 gram of organic compound gave 50 ml of nitrogen. 50 ml of nitrogen collected at 300 Kelvin. 50 ml of nitrogen at 300 Kelvin. and 715 millimeter pressure. Calculate the percentage composition of nitrogen in the compound, and given is aqueous tension at 300 Kelvin is 15 millimeter of Hg. Okay, so let's go for the calculation. We are knowing this formula, PV is equal to nRT. From this I can find number of moles is equal to PV upon RT. So we have to apply formula P1 V1 T1. R is constant, so P1 V1 T1 is equal to P2 V2 T2. P1 V1 T1 for experimental condition and P2 V2 P2 for STP or NTP condition. There is no big difference between STP and NTP. Okay, so pressure given is, total pressure is 715 and aqueous tension is 15. Means out of 715, 15 pressure is created due to the water vapor. So remaining 700 is due to the nitrogen. So P1 I will write here 700. Volume is given 50 ml and experiment performed at temperature 300 Kelvin. So divided by 300 is equal to, pressure is 1 atm is 1 atm. So I will write here 760 millimeter of Hg. Volume we have to find, volume nitrogen we have to find, divided by temperature at STP is 273 Kelvin. Okay or not? It's 273.15. I'm ignoring 1.15. Is it clear now? From this I can find volume of nitrogen. So volume of nitrogen N2 is going to be, cross multiply there, so 700 into 500 into 273 divided by into 50 also. Sorry, this is 50. Sorry, this is 50. 700 into 50 into 273 divided by 300 and 760. This is the volume of nitrogen. From volume of nitrogen we can find moles of nitrogen. How to find moles of nitrogen? N2, moles of N2 divided by 22,400. Why 20,400? Because I took volume in ml. From this I can find total weight here N2. How we can find N2 given means multiply by 28. The total mass, mass of nitrogen. Mass of nitrogen is given. Now we calculated. Now total mass given is 0.3. So mass of nitrogen divided by the total mass 0.3 multiplied by 100. This is the percentage of nitrogen. So method is very simple. You have to write equation here. P1 V1 T1 for the experimental condition, P2 V2 T2 for NTP condition, and from this you can find volume of nitrogen. From the volume of nitrogen you can find moles of N2. From moles of N2 you can find mass of N2. Is it clear or not? And for this mass of N2 we can find percentage of nitrogen. How to find? Total mass upon organic mass multiplied by 100. Is it clear or not? Here it is N2, so don't forget we have to multiply it with the 28. The most important thing is they are giving total pressure here 715, but this total pressure is not because of only nitrogen, it is because of nitrogen plus water. So total mass, so pressure due to nitrogen will be total pressure minus pressure due to the water vapors. This is the most important point here. The total pressure is 715. It is because of N2 nitrogen gas plus water vapors. If I subtract the pressure of water vapor, then remaining is the pressure due to the nitrogen. Is it clear or not? Next is question based on the Geldar's method. They are saying that during the estimation of nitrogen present in an organic compound by the Geldar's method, ammonia evolved from 0.5 gram of compound in Geldar's estimation of nitrogen neutralizes 10 ml 0.1 molar sulfuric acid. 10 ml 0.1 molar sulfuric acid means 10 into 1, 10 millimole of sulfuric acid required to neutralize ammonia evolved. So just write the balanced reaction and get the answer. NH3 plus SO4. So each H2SO4 will consume 2 ammonia molecule to give ammonium sulfate, NH4 twice SO4. They are saying it 10 millimole of sulfuric acid is required to neutralize this ammonia. Is it clear or not? So 1 sulfuric acid means how many moles of ammonia? 1 mole of sulfuric acid means 2 moles of ammonia. So 10 means NH3 is 20 millimoles. 20 millimoles of NH3 present there. But we have to find percentage of nitrogen. So you can observe here 20 millimole of NH3 means 20 millimole of N. 20 millimole of NH3. NH3. 1 NH3 contains 1 nitrogen. So 20 millimole of NH3 contains same nitrogen atoms. So I can find mass of 20 into 10 power minus 3 into 40 Why 14 this time? Because this is N. So this is now weight divided by the weight of organic compound given here 0.5 multiplied by 100. This is the percentage of nitrogen. Is it clear now? So this is the problem based on the Gildas method. You know, Gildas method is not applicable for azo compounds, nitro compounds, and the compounds which are containing nitrogen in the ring. Okay or not? Come to the next. Carriers method. Carriers method, it is used for the halogens. Question is given here. In Carriers method of the estimation of halogen, 0.15 gram of an organic compound gave 0.12 gram of AgBr. What they are saying, AgBr is 0.12 gram. So can we find moles of this? Answer is yes. Moles will be given is 0.12 divided by the molecular weight, and Ag is 108 and bromine is 80, so it is going to be 188. This is the moles of AgBr. Now we can find moles of bromine also. Sir, how to find? One AgBr contain one bromine, so this many moles contain exactly same number of bromine atoms. 0.12 divided by 188. Now I'm knowing the moles of bromine, so from this I can find total mass here multiplied by the molar mass, and it is 0.12 divided by 188 multiplied by bromine. I said earlier it is 80. Got the concept now? Divided by the total. So percentage of bromine is going to be total weight. What we calculated there, percent bromine is going to be 0.12 multiplied by 80 divided by 188. This is the mass for bromine part. Now organic compound is 0.15 divided by and multiplied by the 100. In this way we can find percentage of bromine. But concept I'm saying here is from the given mass of AgX, it may be AgCl, AgBr or AgI, find the moles of X. From the moles of X you can find mass of X, and from the mass of X you can find percentage of X. And how to find mass of the halogen divided by total mass of organic compound multiplied by the 100. Is it clear or not? Next is sulfur. Let's go for the question directly. They are saying in sulfur estimation 0.157 gram of an organic compound gave 0.4813 grams of barium sulfate. Very easy question. What is given there? Barium sulfate, BaSO4 is equal to 0.4813 gram. So moles of barium sulfate is equal to 0.4813 divided by its molar weight. Is it clear or not? How to find molar weight? Beryllium plus sulfur plus 4 times oxygen. It is coming 233. Is it clear or not? Now, so from this barium sulfate I can find moles of sulfur. One barium sulfate contains one sulfur. So this many moles contain exactly same number of sulfur there in terms of moles. So 0.4813 divided by 233. This is the moles of sulfur. So now I can find mass of sulfur. How to find? Multiplied with the molar weight. It is 32 there for the sulfur. Now I'm knowing the weight of sulfur also now, so I can find percentage of sulfur. How to find this? Divided by the total mass given here 0.157 multiplied by the 100. Got the concept or not? Okay, so logic is very easy. Next is phosphorus. In this case also same concept is applied. In case of oxygen, it is 2 methods are there. One is 100 minus percentage of others, or go for this method. Take the organic compound, heat it with the stream of nitrogen, you will get oxygen. Oxygen reacted with the carbon, giving carbon monoxide. Carbon monoxide given reacting with the I2O5 and giving I2. And based on this, we can find the percentage of oxygen in the given organic compound. And last point here. Nowadays we are using CHN elemental analyzer. Very important concept. Nowadays we are using CHN elemental analyzer to find the percentage of carbon, hydrogen, nitrogen. It required very little quantity, only 1 to 3 milligram to display the result. Is it clear or not? So this is also completed. Let's move to the next chapter. What next chapter is? Hydrocarbons. After this, class 11th part will complete it. Okay, after the hydrocarbons. Okay. Hydrocarbons means alkanes, alkynes and aromatic hydrocarbons like benzene and toluene. First is given problem number 9.1. Question is, write structure of different chain isomers of alkane corresponding to the molecular formula C6H14. We have to write different structures for this formula. It is given C6H14. C6H14. Formula itself is saying it is alkane, CnH2n plus 2. Okay. Now we have to find the structures. What is the easier method? Total carbon count is 6. I am knowing it is alkanes, means only open chain possible. Only open chain possible. And all carbon-carbon bonds are sigma bonds only. Okay or not? Total carbon count is 6. So first I can draw 6 carbon chain. 1, 2, 3, 4, 5, 6 carbon chain. Then go for the 5 carbon chain. After 6, next is what? 5 carbon chain. Now in 5 carbon chain, I have to attach one extra carbon. My total carbon count is 6. 5 carbon chain is drawn. 1 carbon is extra. For this one extra carbon, think how many possibilities are there. So one possibility I can connect at this carbon number carbon number 2, and next possibility connect at carbon number 3. Sir, why not this carbon? And if you connect to this carbon, it become previous chain there. If I connect carbon here, like this, it is going to become previous chain. It is already drawn. So what is the method here? I said firstly draw the 6 carbon chain, done. Then next is 5 carbon chain. 1, 2, 3, 4, 5. How many carbon extra? 1 carbon. For this one extra carbon, think about the possibilities. So one possibility I can connect at carbon number 2, and next possibility is I can connect extra carbon at carbon number 3. Sir, this will be same as from this side, it is same as this one. Got the concept? So 6 carbon chain done, then 5 carbon chain also done. What next? 4 carbon chain. Now go to the 1, 2, 3, 4. How many carbons are extra? 2 carbons are extra. So now think about the possibilities. One possibility I can connect 2 extra carbons separately like this, and next possibility I can connect them to the same carbon. These 4 carbon chain also done. Then next, if 3 carbon chain is there, how many carbons extra? 3. So extra carbons are equal to the selected chain or more. Then stop there. Don't go for that. Okay or not? So in this case, I'm getting 1, 2, 3, 4, 5 structural isomers for the given formula. Is it clear or not? In this we can solve for others also. Next is given there. Write the structure of different isomeric alkyl group corresponding to the formula C5H11. Write ionification of the alcohols obtained by attachment of OH group there. So question is very simple. They are saying, let's say we have C5H11 and here something is attached. This something can be OH, this something can be NH2, this can be halogen, etc. Okay na? And you have to find possibilities for the C5H11. Okay or not? So firstly, I'll go for the concept what I said previously. I will go first 5 carbon chain here because it is total carbon count 5. Okay. And based on the formula I'm knowing, it is alkane, it is alkyl group only, means carbon-carbon bonds are sigma. First I'll go for the 5 carbon chain. 1, 2, 3, 4, 5 carbon chain. Then what next? Go for the 4 carbon chain. So 1, 2, 3, 4 carbon chain. How many carbon extra here? 1 carbon. And for this extra carbon, I have only one possibility. Attach at this carbon. Attach this carbon or this carbon. Then go for the 3 carbon chain. 2 carbons are extra. I can attach like this. Okay or not? Now, point is we have to find different possibilities for the attachment of these groups. Okay now, if they're asking number of structural isomers for C5H12, means this alkane, then these three, this hexane molecule, this this pentane molecule, normal pentane, isopentane, neopentane. But question is not about the C5H12. If question is about the C5H10, I have 3 structural isomers: N-pentane, isopentane, neopentane. Is it clear now? But here question is not about the C5H12. Question is, its one hydrogen is replaced by some group, so it becomes C5H11. So now think about the possibilities. Okay or not? One possibility. See, also these 2 carbons are identical. So attach something to this carbon, or this carbon is same. Another possibility, these 2 are identical but different than the previous one. So here I can attach another possibility, and next possibility is this. Use different symbol for different possibilities. So here, if I want to attach alcohol or NH2 or any other group, I have 3 possibilities in the normal pentane part. Come to the next case. Here carbons are identical, so I'll use same. This is different and this is also different. So how many different symbols are coming here? 1, 2, 3, 4. Means in this part I can attach any group in 4 different manners. For the structural point of view, I'm getting 4 different possibilities here. In this case, all these 4 carbons are identical, and I cannot attach anything to this carbon. Sir, why? Because there is no hydrogen to replace. All 4 bonds done by carbon only. So here I will get only one possibility. So how many different possibilities are coming for the C5H11 in terms of the structural isomers? Answer is a 4 plus 3 7 plus 1 8. This is having 8 different possibilities in terms of the structures. Is it clear or not? Then they can ask the kind of alcohol like primary, secondary, tertiary, that you can easily find. Okay or not? For example, if it is alcohol, for amine it is not based on the degree of carbon, so I am writing alcohol part OH. So OH, this is primary alcohol. If I attach here, it is primary alcohol. Attach here is going to be secondary. This is also secondary. Okay or not? These 2 are already done. Same. Likewise here also, this is primary. This is already counted, so don't count it again. This is going to be tertiary. This is going to be secondary. This is going to be primary. Here it is all are same. So one I will write primary. In this way, you can count primary, secondary, tertiary possibilities also. Okay. Next problem. This is very good question. Next problem. Problem number 9.3. Write IUPAC name of the following compounds. Okay, in this case, I'll explain the number 3. They are saying tetraterbutyl methane. Tetraterbutyl methane. So firstly, think about the structure here. First, you can easily write the structure. I'm writing the third one. Tetraterbutyl methane. Okay, so terbutyl methane. This is terbutyl methane part. Okay, what they're saying? Terbutyl methane. Okay, not? So think, how can attach? This is terbutyl. 1 minute. This is terbutyl. They are saying tetraterbutyl means I have to attach 4 terbutyl to the methane part. Okay or not? So what is the important concept here? Observe properly. This thing is terbutyl. 1, 2, 3, 4 carbons. So this is terbutyl. What they say? Tetraterbutyl. 4 terbutyl. 1, 2, 3, 4. Attached to this 1 carbon means methane. So tetraterbutyl methane. Okay or not? Now for this we have to find IUPAC. We have to write IUPAC name. So firstly select the parent carbon chain. Select the parent carbon chain. Is it clear? Now in this case, any selection, like this kind of selection, I can go for this. Okay. Now after this selection, I can observe here numbering 1, 2, 3, 4 and 5. You can observe this is methyl, 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 methyl. So number 2 and number 4 position, they are having methyl groups. So I can write, so and this is what? This is third butyl, and this is also third butyl at number 3 position. Third butyl is given here, third butyl, and you knowing this third is not considered in the alphabetical order for the naming purpose. So I'll take B of this, and methyl I'll take M. Methyl obviously I'll take M. So alphabetically who will come first? Third butyl will come first. So I'll write 3,3. It is a third butyl. It is third butyl. It is complex substance. Is it clear or not? So we have two possibilities for this. One is, let's say this is given. One possibility I can directly write third butyl. Another possibility like this one. Carbon as the parent carbon chain is given number 1. So I can say 1,1-dimethyl ethyl also. Two possibilities are there. So one possibility for this substance is a third butyl. Another possibility is 1,1-dimethyl ethyl. If I'm writing in this manner, I have to keep inside the bracket. Okay or not? So in this case, let's say I'm using third butyl. How many third butyl present? 2. So I will write 2. So it is 3,3-di-third butyl. Okay or not? And methyl. No. Someone is saying, see. If third butyl given, this third is not considered in the alphabetical order. This B will be considered in alphabetical order. If sec or third anywhere, sec or third present, they are not considered in the alphabetical order. So I will consider B of the third butyl in alphabetical order. Got the concept or not? So alphabetically, out of B and M, obviously B is coming first here. This A, B, C, D, you are knowing A, B, C, D, E. Are you understood? Others, is it clear to you? Okay, understood or not? Yes, okay, very good. Chalo. So I will write this as a 3,3 di-third butyl 2,4,4 tetramethyl and total 5 carbons of pentane. Is it clear or not? Okay, got the concept. Or another possibility is, instead of writing third butyl, you can go for 1,1-dimethyl ethyl. Then this D will be considered alphabetic order because this dimethyl ethyl is the name. Okay or not? Next one. Now these two you can solve. IUPAC nomenclature part was taken earlier. Now next is sodium salt, of which acid we needed to prepare the propane molecule. What I want to make? Propane. Okay. So I want to prepare propane molecule. So knowing this concept, if we have RCO, if I heat this with soda lime, NaOH heating done, then this will give compound RH. Means what will happen there? This part and this will come out as Na2CO3. So this H bind with the R and compound is RH. So now we have to think what kind of carboxylic acids can give a propane molecule to us. So let's say we have one. So what I am observing here, this sodium salt of the carboxylic acid is having, let's say, N carbons. So out of N carbons, one carbon is gone as removed as Na2CO3. Means formed alkane is having one less carbon, N-1. Got the concept? So if I want to make propane, I will take carboxylic acid of 4 carbons and sodium salt taken here. So two possibilities are there. One possibility is this butanoic, sodium butanate, and another is this possibility where I have attached this CO minus like this. So it is 2-methyl propanoate. Is it clear? Now, in this first case, if I heat with a soda lime, this part will be removed and this remaining part will give me propane. Here also, if I remove this part by decarbosylation, this is giving me propane. Understood or not? So we can have 2 monocarboxylic acids which can give me propane molecule after the decarboxylation reaction. Is it clear or not? Okay. Again, IUPAC NEET question, I am not discussing it. Next is write structures and IUPAC name of the different structural isomers of alkene corresponding to the C5H10. What to write here? Different structural isomers of alkenes. Formula given C5H10. Then as I said earlier, firstly go for 5 carbon chain, then 4 carbon chain, then 3 carbon chain. Follow that rule, okay? 5 given, so I'll go for 5 carbon chain, 1, 2, 3, 4, 5 carbon chain. Then 4 carbon chain, 1, 2, 3, 4 carbon chain, 1 extra carbon attached here. And then 3 carbon chain, 1, 2, 3 and 2 extra carbon attached like this. But now question is not about the alkanes here. It is alkene, means we have to make double bond there, carbon-carbon double bond there. So now in this 5 carbon chain, think different possibilities for the double bond. So here, observe, if I draw double bond here between these 2 carbons or between these 2 carbons, same. So one possibility is this, another possibility is this. So in this, if I want to draw double bond, I have 2 possibilities in terms of the structural. If they are asking including stereo, then I have to go for geometrical isomers also. Okay, so I can draw double bond here or here is same, one possibility. Writing double bond to this place or this place is same, so second possibility. Got the concept or not? Come to the next case. Here, if I draw double bond at this place or this place, these 2 are going to be same. Writing double bond here or here is same. Okay or not? Next possibility, this one, and next possibility, this one. So how many possibilities are there for the double bond? Answer is 3 in this case. The total possible alkenes are 5 in terms of the structures only. Got the concept? So you can observe there 1, 2, 3, 4, 5. So instead of writing this many structures, directly go for this method what I said to you. Okay or not? Firstly, write the 5 carbon chain, then 4 carbon chain. Now come to this case. Sir, why are you not considering this? In this case, can I draw double bond? Okay, let's draw it. How many bonds coming around carbon? 1, 2, 3, 4, 5. Possible? Not possible. So this will not give any double bond case. Understood the method or not? So don't write multiple structure. Don't waste your time here. Okay. Time is very precious in the exam. What to do there? Go for the method what I said here. Firstly, I write the 5 carbon chain, then go for the 4 carbon chain and make different symbols for the different possibilities. In this case, we have to think about double bond. So one possibility for double bond, second possibility for double bond. Is it clear or not? Okay. Likewise, here also we can go for the multiple possibilities. Got the concept? Understood? Okay, very good. Next one. Now question is, draw cis-trans isomer of the following compounds. Also write their IUPAC names. Okay, so what is given here? CHCl double bond CHCl. So one possibility is C double bond CH. They are saying cis-trans. So this is a cis isomer and this one is trans isomer. Cannot come to the name nomenclature here. So in this case, it is what? 1,2-dichloroethene, 1,2-dichloroethene. But this is cis form, so I'll name it as cis 1,2-dichloroethene. This is trans form, so I'll name it as trans 1,2-dichloroethene. Got the concept? Now that's what you can check also. They're writing cis 1,2-dichloroethene and trans 1,2-dichloroethene. So point is very simple. You have to write name cis and trans also in the IUPAC nomenclature if they are giving geometrical form there. Got the concept or not? Likewise, next molecule given there, CH3C, CH3. So okay, C2H5C, CH3 double bond. Okay. So C double bond C. What is attached here? CH3. C2H5, so I will write C2H5 as CH2, CH3. Any problem? This side CH3, C2H5 I am writing as a CH2, CH3. This is the cis isomer. Trans isomer I can write like this: carbon-carbon double bond, CH3, 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 CH3. Okay. Okay. Now C2H5 I will write CH2, CH3 here. And here also I will write CH2, CH3. Now, firstly, for the nomenclature, I have to select the parent carbon chain. This is parent carbon chain. Numbering from any side is same. So 1, 2, 3, 4, 5, and 6. Is it clear or not? So what I can say, this is a hexane. Hex and 3 position is in. So hex 3 in. But 3 and 4 position having what? Methyl group also. Methyl is substance we have right before word root. So I will name it as 3,4 dimethyl hex-3-ene. Now point is this is cis isomer. So before this complete name I will put cis there. So I will name this as actually cis 3,4 dimethyl hex-3-ene. Got the concept or not? And for this case, I'll write a trans before the name. That's what you can check. They're writing there. They're writing cis 3,4 dimethyl hex-3-ene. Got the concept now? So what is the important concept here? This is okay, no problem. 3,4 dimethyl hex-3-ene. But before that, what to write there? Cis, and in this case, what to write? Trans. So what is the important concept we are learning here? If they are giving geometrical form of the any molecule like cis or trans, don't write only the name of the word root and remaining part. Write the cis or trans isomer also before the name. Okay or not? Here, like if I'm writing 3,4 dimethyl hex-3-ene, this is not enough for the nomenclature. We have write cis or trans isomer also. Got the concept? Okay. Come to the next case. Okay, next question. Okay. Write IUPAC name of the products obtained by addition of HBr to the hex-1-ene in the absence of peroxide and in the presence of peroxide. First of all, I will write the structure of hex-1-ene. CH3 1, 2, 3, 4, 5, 6. Hex-1-ene is written here. Now two conditions are given. One is HBr with peroxide and another is HBr without peroxide. Okay, let's go for this. HBr is given, peroxide not given. If peroxide not given, I will break HBr as plus and minus. If peroxide not given, I will break HBr as H plus and Br minus. If it is giving ions, pi bond will also break in heterolytic manner to give plus and minus polarity there. So here, if I am breaking bond like this, okay, or I will make it easier. This pi bond is breaking and binding with the H plus, binding with the H plus. Got the concept or not? Pi bond is breaking and binding with H plus. Now when binding with the H plus, I have two possibilities. One possibility, H plus bind to the CH2 carbon plus develop on the CH carbon. So I will write two possibilities are there. Let's say H plus is binding to the CH2 carbon, then plus develop on the CH carbon. Na? So 1, 2, 3, 4, 5, 6. This plus develop. Another possibility is keep H plus, this H plus bind with the CH carbon. If binding with the CH carbon plus develop on this CH2 carbon. So 1, 2, 3, 4, 5, 6. H bind with this terminal carbon. So with this second carbon plus develop on this first carbon. Now for this carbocation, I have 3 plus 2, 5 alpha H. And for this one, I have only 2 alpha H. So this carbocation is more stable. So this will form. Okay, na? So this will give major product. Br minus will attack on this carbocation and I'll get product here 1, 2, 3, 4, 5, 6. And bromine, this is my major product. I will make it easier by taking one simple example. This is taken. CH double bond CH2 taken and HBr is given to us. Peroxide not taken. So I will write this as H plus and Br minus. After this, I will break pi bond, bind with the H plus. Break pi bond and bind with the H plus. Now, if H plus binding to the CH2 carbon plus double upon CH carbon and H plus binding to the CH carbon plus double upon CH2 carbon. So go for the both possibilities. H plus binding with the CH2. Then I'll get this carbocation. H plus binding with this. I will get this carbocation. Now think out of these two who is more stable. So obviously first is more stable. So this will give you major product. Br minus attack here. Same logic applied in this case also. This is about the HBr without peroxide. Sir, what if peroxide given? So if peroxide given, very easy method is there. Okay, peroxide given 1, 2, 3, 4, 5, 6. Double bond. Condition is given HBr peroxide. When peroxide given with the HBr, it is giving Br radical. What is giving? Br radical. Obviously, peroxide will help to generate the Br radical. Okay, now break this pi bond in homolytic manner. Sir, why homolytic manner? Sir, it is a radical na bhai. Radical is promoting homolytic bond fission here. So after bond breaking, method is very easy. Just tell me one thing. Where radical is more swell? This is carbon number 1, this is carbon number 2. Where radical is more swell? Radical is more swell on carbon number 2. Radical is more swell on carbon number 2. So Br bind at carbon number 1, opposite. Radical is more stable at carbon number 2. So Br bind at carbon number 1. Radical is more 1, 2, 3, 4, 5, 6. Radical is more stable at carbon number 2. So Br bind at carbon number 1. Is it clear or not? This is the product here with peroxide. Got the concept or not? Okay. So this is very good question. They are considering the peroxide effect also. Okay. Next one. Write the structure of different isomers corresponding to the fifth member of alkyne series. They are saying fifth member of alkyne series. So first of all, we have to find the formula of the fifth member. And to find the formula of fifth member of alkyne series, we need to know the first member here. If you knowing first member, then only you can think about the fifth member. Am I right? So alkyne, first alkyne is ethyne. First alkyne is ethyne. This is first alkyne. Now you're knowing first alkyne, so you can think about the fifth alkyne. Sir, how? First alkyne has how many? 2 carbons. First alkyne, 2 carbons, means 1 extra carbon. No? First alkyne, 2 carbons. Second alkyne, 3 carbons. Like that you can go. So if I'm reaching to the fifth alkyne, first alkyne has 2 carbons, 1 extra. So fifth alkyne, how many carbons? 6 carbons there. So C6. H. General formula of alkyne CnH2n minus 2. So 6 into 2, 12 minus 2 is going to be 10. Got the concept or not? CnH2n minus 2. So 6 into 2, 12 minus 2, so 10. This is the formula there. So first of all, we need to find the formula. Then the remaining is very easy. It is 6 carbon alkyne. 6 carbon alkyne. Method I said go for now 6 carbon. So firstly go for 6 carbon chain. Done. Then go for 5 carbon chain. In this 5 carbon chain, I have to attach 1 extra carbon. So 2 possibilities are there. Am I right or not? Then go for 6 carbon chain, 5 carbon chain. Then go for 4 carbon chain. Then go for 4 carbon chain. So 1, 2, 3, 4 carbon chain. 2 carbons are possibly attached to same carbon like this, and another possibility attached to different carbons like this. But now question is not about the alkane in this case. Question is about the alkynes. Means I have to draw carbon-carbon triple bond. What to draw? Carbon-carbon triple bond. Now point is how we can draw. So instead of wasting time, I said one method, make symbols. Let's go for that. Here, writing triple bond to this place or this place is same. So one symbol for this. Triple bond between these 2 carbons and these 2 carbons identical. Next possibility and next possibility is here. So in this 6 carbon chain, I can have 3 possibilities for the triple bond. Okay or not? In this case, here I cannot write any triple bond. Let's write triple bond there. How many bonds will come around this carbon? 5 now. Possible? Not possible here. So in this part, I cannot, in this part, triple bond not possible. Ignore it. Okay or not? So I will write it again for the better clarity. It was given here 1, 2, 3, 4, 5 like this. So here in this part triple bond not possible, here also not possible, here also not possible. Is it clear or not? In this part I cannot draw any triple bond there. Here I can draw triple bond. Yes, am I right? So one possibility is this and next possibility is here I have 2 possibilities for the triple bond. In this case, in this region triple bond cannot be drawn. Let's see how many bonds present here? 3. If you draw triple bond, means you have to write 2 more bonds there. 3 plus 2, 5. 5 bonds around carbon, not possible. So this part cannot have triple bond. Only this part can have. So this or this identical. So I have one possibility there. This case, in this region, triple bond not possible. Logic is same. And here, triple bond possible. So this is one possibility. I will directly write here. This is one possibility here. In this case, 3 bonds present here. If I draw triple bond, it becomes 5. Here also 5. So it is not possible to draw triple bond there. So these are the possibilities for the alkynes in this case. So 3 plus 2 plus 1 and 1. Is it clear or not? So you can check it here. So 7 came there. Let's count it. It is giving me 1, 2, 3, 4, 5, 6 and 7. So instead of writing this many structure, follow the method what I said. Got the concept? Understood? Understood? Yes or no? Okay. Chalo. Next question. How will you convert the ethanoic acid into benzene? Very good question. Ethanoic acid into benzene. Ethanoic acid into benzene. Ethanoic acid is given. And from this, we have to prepare benzene. From this, we have to prepare benzene. So first of all, I will go for the decarboxylation reaction, soda, lime, and heating. This will give me methane. From methane, I can prepare methyl halide, let's say methyl chloride, by providing Cl2 in the presence of light, free radical substitution reaction. Methyl chloride can be used to prepare ethane. How? Answer is by sodium dry ether. Ethane to ethyl chloride by Cl2H nu, free radical substitution reaction again. From this I can make alkene, CH2 double bond CH2 by giving alcoholic KOH. This alkene to vicinal dihalide, like vicinal dichloride, by giving Cl2 in the absence of light. Then I can make ethyne from this. How to make ethyne? Firstly give alcoholic KOH, and then soda lime NaNH2. Heating also required for both cases. And then this to this pass through red hot Fe tube. Is it clear or not? In this we can make it. So technically, if I am able to make this ethyne, I can get benzene by the aromatization reaction, by this cyclic polymerization reaction, by passing this thing through the red hot Fe tube. Got the concept or not? One more point here. Here I prepared ethane by firstly going for the decarboxylation, giving methane to methyl chloride, free radical substitution reaction, then ethane by the Wurtz reaction. One more possibility is there. Directly go for the coal-based electrolysis. By coal-based electrolysis, what is happening? If it is coal-based electrolysis, RCO minus Na plus. Going for the electrolysis, what is giving? RR na? CH3 combine and giving ethane. Remaining story is same. Got the concept? So that's how we can convert ethanoic acid into the benzene. Okay? Understood? Okay, chalo, very good. Nomenclature part discussed. Okay, let's quickly brief the reactions of this chapter. In case of alkanes, let's listen quickly. In case of alkanes, for example, CH4 given, or for example, ethane given, all bonds are sigma bonds only, and polarity is also not present. That's why they are least reactive organic compounds. They are known as paraffins also, because in ordinary conditions they are non-reactive towards acids, base, and other reagents. They are going for free radical reaction. So for example, we have this molecule isopentane. And now condition is given Cl2H nu. Condition is given Cl2H nu. So they can ask here ki how many monochloro products are possible. Monochloro products are possible. Then two possibilities are there. They can ask structural monochloro or they can ask monochloro including stereo. Okay, so what is the method there? I have to bind one chlorine in this. So I said some symbol method. These two carbons are identical. This carbon is different than the previous two. This is different and this is also different. So as per this symbol, I can get this compound. As per this symbol, I can get this compound. According to this symbol, this one I can get this compound, and as per this, I get this compound. So if they are asking how many monochloro structural products are coming for this compound, answer is here 4. But if they are asking including stereo, then check chiral center also. So in this case, this is chiral center. So this compound plus its mirror image. In this case, no chiral center. In this case, this carbon is chiral center, so this plus its mirror image. So if question is there, how many monochloro structural products for this isopentane? 4. Number of monochloro products including stereoisomer 4 plus these two mirror images, so answer will be 6. Got the concept or not? Alkanes are going for many other reactions also. For example, let's say normal hexane taken 1, 2, 3, 4, 5, 6. I am giving chromium oxide supported over alumina gel at high temperature and high pressure. This will give benzene molecule and release hydrogen gas, going for this aromatization reaction. In the place of chromium oxide, we can take molybdenum oxide or vanadium pentaoxide also will give benzene. Next possibility. In case of alkanes, let's say 6 carbon chain is given. If I am giving AlCl3 HCl, they can go for isomerization also and will give a 6 carbon chain given, so will give 5 carbon chain as major product. 6 carbon chain given, then give 5 carbon chain as a major product. Got the concept or not? So isomerization reaction is also possible in case of alkanes. Got the concept? Understood or not? Okay. For hydrocarbons, one very important point, if for complete combustion, they will give you carbon dioxide and water. And if they are going for incomplete combustion, they will give you carbon black and water. So remember always directly, if hydrocarbon, for example, alkane, going for complete combustion, what you will get there? CO2 and H2O. Incomplete combustion, carbon black and water. Is it clear? Okay, next possibility. This hydrocarbon, for example, CH4, can go for controlled oxidation also. For example, oxygen limited supply given, and by taking different catalysts, I can prepare different organic compounds here. Is it clear now? So it can go for controlled oxidation. Very important reaction is there. If you have 3 degree hydrogen, and giving strong oxidizing agent, for example, KMNO4, then this 3 degree hydrogen CH bond get oxidized and giving us alcohol. In case of alkenes, they are having pi bond, and that is why they can go for addition reaction. It is a carbon-carbon, it is a non-polar pi bond. Non-polar pi bond is acting as a nucleophile, so we'll react with the electrophile, can go for electrophilic addition reaction. If electrophile given E and U, I am writing reagent part here, pi bond break and bind with the electrophile. Okay, here I have two choices. E plus bind with the CH2. If E plus bind with the CH2 carbon plus double upon this, another possibility is ki E plus binding to the middle carbon, then plus double upon this terminal carbon. Out of first, second, which plus is more stable? So obviously first is more stable. This will decide major product. Next concept, nucleophile attack on this plus, and by the attack of nucleophile, I will get here this compound here. If E plus is chlorine plus, make it simple, halogen plus, then here it will be Cl. In this case, this will go for this kind of ring formation which is known as cyclic halonium ion. So in case of chlorine plus electrophile, cyclic halonium ion will form, not carbocation, and that's why in this case rearrangement not possible, while other cases rearrangement is possible if I am able to increase the stability of carbocation by alkyl or hydrogen shift. Is it clear? Okay, then we can go for multiple reactions. This propene is taken, let's say I am giving HBr. So always think after the breaking of pi bond, if I'm breaking this pi bond, where plus is more stable for the electrophilic addition reaction. So in this case, after breaking of pi bond, plus more stable on this middle carbon. So Br bind here, Markovnikov product this will form. If diluted sulfuric acid given, so dilute sulfuric acid given means it is addition of water. I can simply write H2H plus here. So in this case, OH bind to this carbon, this alcohol will form. If concentrated sulfuric acid given, so concentrated sulfuric acid will give me H plus and HSO4 minus. And always remember, if I want to go for the addition of sulfuric acid, I will use concentrated sulfuric acid but cold condition. If hot condition taken, then it can go for the free radical reaction. So here anionic part is what? HSO4 minus. This bind to the more stable carbon, I'll get OSO3H. OSO3H. Got the concept or not? Dilute sulfuric acid taken means water is more. It is addition of water. Concentrated sulfuric acid taken means it is sulfuric acid is more. It is addition of sulfuric acid. Okay or not? In case of addition of sulfuric acid, we have to take cold condition. Otherwise, it can go for free radical substitution reaction. One more point. For the dilute sulfuric acid, we can add, if I want to take dilute sulfuric acid, one more possibility is there, add a few drops of concentrated. If you add few drops of concentrated sulfuric acid, it automatically become dilute sulfuric acid. Okay or not? Next possibility. Let's say halogen is given, H2 given, condition is a dark and cold. Sir, why dark and cold? If light taken, then halogen will prefer free radical reaction. That is why dark and cold taken, because I want to go for electrophilic addition reaction. So in this case, it is XX. So plus part is X, minus part also X. So here after binding of pi bond, one position is having X, another position also having X. Will get this vicinal dihalide. Is it clear now? Why dark and cold taken? To avoid the free radical substitution reaction. For example, if this alkene is reacting with the X2 in the presence of light, in this case it will generate X radical, which will bind with the carbon by breaking CH bond. So here this CH bond breaking is giving me most stable radical. So here X will bind at this alpha position or allylic position that is known as allylic substitution also. Okay or not? One more point I said few minutes back, if HBr given like this, H plus Br minus pi bond break, bind with H plus carbogran double upon this middle carbon. So Br is going to bind here in major product. But if they are giving HBr in the presence of peroxide bond, this will generate Br radical. This will promote homolytic bond fission of the pi bond. And here I am knowing radical is more, this is 1 and this is 2. Radical is more stable on 2. So Br bind at 1. So I'll get this product in this case. And always remember, if X2H nu given, break CH bond. X2H nu given what to break? CH bond. Okay or not? And if HBr peroxide given, then go for homolytic bond fission of the pi bond. And for this case, if radical is more stable at 2, bind bromine at 1. In some other case, if it is the radical is more stable at 1, bind bromine at 2. Means HBr peroxide is very simple. In a bond, let's say HBr peroxide, I am saying HBr peroxide. In HBr peroxide, break pi bond, homolytic bond fission. If radical more stable on this carbon, bind Br here. If radical is more stable on this carbon, bind to another one. This is the HBr peroxide reaction. Is it clear now? Alkyne also having same kind of reaction. Okay. They are also having electrophilic addition reaction. For example, HBr given, pi bond is breaking, binding with H plus. Where plus charge more stable? Obviously this middle carbon. So Br minus bind to this carbon in major product. Now one more pi bond left, so same reaction repeated one more time. So by the first reaction, what I am observing? Bromine binding the middle carbon now. So don't waste your time, directly go for the product. One more pi bond present, same reaction repeated one more time. By the first reaction, I am knowing Br binding to the middle carbon. So by next reaction also Br binding to the middle carbon, I'll get this geminal dihalide here. Understood the concept or not? If they are giving carbon triple bond carbon and saying addition of water, means what, take dilute sulfuric acid. In this case, catalyst Hg2 plus required. Same concept here also, pi bond break and bind with H plus. Water taken, so H plus will be actually H3O plus. So who is providing H plus? Actually H3O plus is providing H plus here. Got the concept now? Then same logic here. Where plus charge is more stable? Middle carbon. So I will break one pi bond and bind OH to this. Now this is enol. Enol will go for tautomerism, and by the tautomerism this ketone is formed here. This is the reaction here for the alkyne also. Understood or not? Okay. And one very important concept. When alkene is given, I am giving X2 in dark and cold condition. Dark and cold condition to taken is to avoid free radical reaction there. What is happening there? XX is binding to the vicinal position. I am getting vicinal dihalide. Here this X2 cannot be F2. Why cannot be F2? Because fluorine is highly reactive. If fluorine taken, instead of getting vicinal dihalide, I will get carbon black and HF. It can be Cl2 or it can be Br2 also. It cannot be I2 in ordinary condition. I2 in ordinary conditions. Sir, why? Because if two iodine present in the adjacent atoms, they are highly unstable. This is removed and again converted back into the original substrate alkene. So point is, when you are adding iodine, problem is two iodine on adjacent atoms are highly unstable. So this will break and convert it back into the alkene. So addition of iodine to the alkene, addition of iodine to the alkene is not possible in normal conditions. Reason, in normal conditions this vicinal diiodide will break and will give you alkene. So finally there is no product formation. Okay. Now in case of aromatic hydrocarbons, if I want to make benzene, then we have multiple methods. For example, if phenol is given, phenol to benzene by giving zinc dust. Zinc dust is the only reagent who can break carbon oxygen bond of phenol. If sodium benzoate is given and I want to make benzene, then I can go for decarboxylation reaction, soda lime calcium oxide heating. If I have this compound acetylene, from acetylene to benzene, red hot Fe tube condition, cyclic polymerization. If I have hexane, normal hexane, this to this, chromium Cr2O3, chromium oxide supported by alumina gel, high temperature and high pressure, means aromatization reaction. And in case of benzene, what kind of reactions are there? Electrophilic substitution reaction. So if electrophile given, it is going to bind there. HNO3 plus H4. This will give nitrobenzene. It will give nitrobenzene. If CH3Cl, given, this will give PSCH3 toluene, Friedel-Crafts alkylation. The most important reaction here, let's say N-propyl chloride AlCl3 given. In this case, Cl migrate towards AlCl3. This will generate this carbocation. This carbon can go for rearrangement, and finally I will get this isopropyl carbocation as electrophile. So this will give me compound isopropyl benzene, also named as cumene. Now benzene is treated with the concentrated sulfuric acid. So concentrated sulfuric acid is giving electrophile SO3, binding there and giving compound SO3H benzene sulfonic acid. Now come to the most important reaction for the benzene. Benzene is reacting with the Cl2 in the presence of AlCl3, dark and cold. Again same point here also. Why dark and cold condition taken? Because I want to avoid free radical reaction. I want to go for ESR. Cl2 taken, Cl2AlCl3, this will generate electrophile Cl plus. In benzene all the sides are identical, bind chlorine there. Got the concept or not? Now if same conditions taken, Cl2 dark and cold, but difference is now this chlorine is taken in excess. So if I am taking limited quantity of chlorine, ESR happen only once. But I am taking large excess of the Cl2, dark condition, cold condition, AlCl3, Lewis acid taken. So here large number of Cl plus generated and ESR will happen 6 times. And I will get this compound C6Cl6. What I'll get here? C6Cl6. And this compound is named as hexachlorobenzene. This compound is chlorobenzene. This is now hexachlorobenzene. 6 times ESR happen. Now, if light taken, then what will happen? Let's observe. Cl2 taken in the presence of light. Then pi bond of benzene will break. And after breaking of pi bond, Cl bind there. So it is going to have 6 Cl, each carbon 1 chlorine and 1 hydrogen already present. In this case it is breaking pi bond, so CH bond remains intact there. I will get this compound C6H6Cl6 named as benzene hexachloride. Name is benzene hexachloride, but there is no benzene structure. It is actually having cyclohexyl ring there. Got the concept or not? So these are the important reactions for the benzene. Okay. Now come to the next chapter or first chapter of the class 12th. Haloalkanes and haloarenes. Haloalkanes and haloarenes. Okay. Take a break of 5 minutes. So it's now 10:55. So we'll resume class at 11 o'clock. Okay. But just confirm once again, audio, video, okay or not? Okay. So same. So just now I got one message that all of you are listening properly. You are very attentive. That's good. I appreciate this. Now, so what basically we are doing actually here? We are actually trying to cover the NCERT. Because you're knowing they are asking question from NCERT only, na? So it is better to be more focused in this stage in NCERT part, okay? Instead of reading unnecessary stuff at this moment, it is just be focused on the concepts which are required for our exam. We are preparing for NEET exam. Here we are not doing any PhD. We can read anything randomly which is given in any book. We have to be very concise in this moment, okay? Like in many places, what I had observed, they're wasting so much time on unnecessary things which are not relevant with the NEET exam. Just to show off. Okay, I'm knowing this much. Here in Srigo slides, we are just be more focused to explain only those concepts which are required to you, not to show off my knowledge or other colleagues of the same. Okay, means our institute. We are more focused to emphasize on those points which are relevant for your exam, na? Because time is limited and now it is very limited. And we are very focused then, and if I'm at the stage of 300, 400, 200 also, if I'm reading next 1 month in a well prepared manner, in a focused manner, only relevant content, then I can achieve 550, 600 like that also. If I'm at 550, 600, I'm doing well, I'm focused only on the relevant concepts, then I can go to the 700 also, because they're not asking beyond this layer. So in this stage, those who are listening to me, I'll suggest only one thing. Just be focused on the only those concepts, those points which are relevant to your exam. Technically, I'm saying focus on NCERT only. NCERT, NCERT, NCERT. For you, NCERT is everything. Gita, Bible, Quran. Okay or not? Chalo. So let's start this topic. Haloalkanes and haloarenes. First chapter of the class 12th organic chemistry. Chalo. In this first page only, we have I'm finding few important chemicals written here. In this first page, first paragraph only, they are writing few important chemicals related to the halogens. 1, yes, very good, very good. So radical bind at 1. So product is going to be pH, CH2, 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 Br. Got the concept or not? Yes, chalo, theek hai. CH bond is breaking if CH bond is breaking if H2H nu given. In H2H nu breaks CH bond at alpha position, this CH bond. H2H nu given, then break CH bond at alpha position. HBr peroxide given, then break pi bond. HBr peroxide then break pi bond. In this case, go for opposite. If radical is motional here, like in this case, radical is motional on carbon number 2, so bind Br at carbon number 1, opposite. Okay, okay. H2H nu given, break CH bond. For double bond, break at alpha position. Br2 peroxide given, break pi bond. And go opposite. If radical is motional at 2, bind bromine at 1. Understood or not? Don't forget these two cases. Chalo, next case. Question is, oh my God. Why sulfuric acid is not used during the reaction of alcohol with the Ki? You're knowing, when I'm reacting alcohol with the HX, this HX, when I'm reacting, 1 minute. When alcohol is reacting with the HX, it is giving RX and H2. This HX can be HCl, this HS can be HBr, and this HS can be HI. In case of HCl, reactivity is low. So if it is a primary alcohol or secondary alcohol, then taking catalyst ZnCl2 is mandatory. Tertiary alcohol, catalyst is not required. HBr, HI, the reactivity order of HCl to HI is, as we are moving from HCl to HBr, HBr to HI, reactivity increases. So for HBr, HI cases, catalyst not required. In case of HCl, catalyst is required if alcohol is primary or secondary. For tertiary alcohol, alcohol itself is sufficiently reactive, so catalyst is not required to perform the reaction. HBr is prepared by ionic bromide, for example, sodium bromide with a sulfuric acid diluted. HI is prepared by taking ionic iodide, for example, NaI or Ki with the H3PO4. Now, what they are asking here, why sulfuric acid is not used for the preparation of HI in this case when you are reacting alcohol with the Ki or NaI? Because if sulfuric acid taken, it will oxidize I minus into I2. And our target is here not to prepare I2. Our target is here to prepare HI. So simple answer is H2SO4 is oxidizing agent, that's why not, is strong oxidizing agent, that's why not taken here. Is it clear or not? Otherwise it may oxidize I minus into I2, I'll not get HI there. Next is write structures of different dihalogen derivatives of propane. See, I say one concept to you. If they are asking monohalo products, then you can go for symbol method. But if they are asking dihalo, trihalo like that, then we need to write the structures. Okay or not? So now, here it is, write the structure of different dihalogen derivatives of propane. So first of all, I'll tell you monohalogen. In propane, 3 carbon chain is the only possibility. Monohalogen, so one possibility, at these identical, this is possibility. Here I can get 2 monohalo compound, N-chloropropane and 2-chloropropane. But now question is not here monohalo, question is a dihalogen compound. So propane is given and here I have to attach 2 halogens. It is very easy. Firstly think, if you are going to attach 2 chlorine on different atoms, 2 chlorines on different atoms, then possibilities are 1, 2, 1, 3. Getting or not? I am going to attach 2 chlorines on different atoms, then 1, 2, 1, 3. So 1, 2, one possibility, 1, 3, another possibility if you attach to the different atoms. Now second possibility, think, if I am going to attach to the same carbon, if I attach 2 chlorines to the same atom, then attach at 1, 1, another possibility attach at 2, 2. Don't say attach at 3, 3. Don't say this like attach at 3, 3 is same as attach at 1, 1. Now if you are writing here, it become number 1 now. Are you getting or not? So how to solve this kind of problem? Is it clear? Firstly think, if I attach 2 chlorines to different atoms, then what are the possibilities? Attach 1, 2, attach 1, 3. If I want to attach 2 chlorines to the same atom, then 1, 1, 2, 2. This is same as first one, 1, 1. What the concept now? Means what I can get here, as per 1, 2, I can get this compound, as per 1, 3, I can get this compound, 1, 1, this compound, and 2, 2, this compound. Is it clear now? So here both chlorines are attached to the different carbons, attached to the different carbons, attached to the same carbon, here attached to the same carbon. So these are 4 different dihalogen derivatives of the propane. If they are asking question structure only, then 4, no problem. And assume they are asking including stereoisomer. They are saying in the question including stereoisomer. Then we need to check chiral center also. Is it clear or not? And for chiral center cases, add 1 mirror image. Okay or not? Next question is, among the isomeric alkanes of molecule, this identify that one photochemical coordination yield a single monochloride, 3 isomeric monochloride and 4 isomeric monochloride. So C5H12, same symbol method will work. C5H12, 1, 2, 3, 4, 5. Then 4 carbon chain and then 3 carbon chain. Now in first case, how many different symbols are possible? These 2 identical, these 2 identical, this is different. 3 possibilities. Here these 2 identical, this is different, this is different, this is different. 4 possibilities. Here all 4 identical, and I cannot attach halogen to the middle one because no hydrogen to replace, means only 1 possibility. So now they are asking Among the isomeric alkanes, like normal pentane, isopentane, alkane molecular formula C5H12 means N-pentane, isopentane and neopentane. Identify one that on photochemical chlorination yield single monochloride. Single monochloride means neopentane. 3 isomeric monochlorides. First one, normal pentane. 4 isomeric monochloride, isopentane. Very easy question. By symbol method you can solve like this. Got the concept or not? Next question. Draw the structure of major monochloro products in each of the following reaction. Each of the following reaction. What is given? SOCl2 given. You are knowing this reaction. ROH, ROH2, RCl. One possibility SCl. SCl catalyst and Cl2 required for 1 degree, 2 degree. Another possibility, one possibility is this one. Next possibility, we can use PCl3. Next possibility, we can use PCl5. Next possibility, we can use SOCl2. Out of all these, the best one is SOCl2, because in case of SOCl2 byproducts, SO2 and SCl are gaseous. So PCl3 byproduct is S3PO3. In case of PCl5 byproduct is what? POCl3 and SCl. Now given question is what? OH plus SOCl2. What will happen? This SO and this O, they will come out as SO2 SCl. So this will give compound chlorocyclohexane plus SO2 and SCl as a byproduct. Got the concept or not? Next question. What is given there? Br2 heat or light. What I said, X2H nu given. What to break? CH bond. What to break? CH bond. X2H nu given. What to break? CH bond. HBr peroxide given. What to break? Carbon-carbon pi bond. X2H nu given. I will break CH bond. Now in this given compound, point is which CH bond I have to break. So answer is, this is alkene, this is benzene, so I can write double bond here. This is alpha carbon, so break alpha CH bond. What to break? Alpha CH bond. What to break? Alpha CH bond. Got the concept or not? So in this case, what to break? Alpha CH bond and bind halogen there. Got the concept or not? Next is given HCl OH heat given. So this reaction is written here, ROH become RCl. So in the place of OH, Cl will come. But now important part. This OH is attached to the benzene, and if OH is attached to the aromatic ring or any double bond, this is going for the resonance and having partial double bond character. And that is why this carbon-oxygen bond of phenol we cannot break by any reagent except a zinc dust. So they can ask one question also, who can break carbon-oxygen bond of phenol? Answer is zinc dust. Who can break carbon-oxygen bond of phenol? Answer is zinc dust. So if I am giving this compound, observe this compound, here we have this thing, they are giving a structure here, OH, CH2H. Now it is treated with the HCl. So this carbon-oxygen bond will break. So in the place of OH, what I will get here? Cl. But this carbon-oxygen bond will not break. Or carbon-oxygen bond of phenol we can break only by zinc dust. Okay. Next reaction is given. This is repeated many times. This is given plus Hi. So compound is given here. Compound is given here. Hi given. Hi given. What to write? Answer quickly. Plus or minus H plus N, H plus N, I minus. What to write? H plus N, I minus. What will happen? Pi bond break and bind with H plus. Pi bond break and bind with H plus. Now answer. Now answer. This is 1 and this is 2. Where carbocation is more, binding with the plus means generate carbocation. Binding with the plus means generate carbocation. Am I right or not? Where carbocation is more stable? Answer quickly. Where? Yes, very good, very good. So carbocation is more stable at carbon number 1. So I'll get this carbocation. What next thing will happen? Now there is no possibility of rearrangement. Directly attack on this and you will get this product here. Next question given. Next question. Assume. Okay. Next question given. CH3, CH2Br, halogen exchange reaction. You are knowing if you have RCl or RBr. Treating with the NaI in solvent acetone, NaI in solvent acetone, then what will happen? The ClBr is replaced by iodine. What I'll get here? Ri. So RCl, RBr given. Treating with the NaI what I'll get? Ri. In this case, byproduct is going to be what? NaCl or NaBr. Logic is very simple here. What is given? Observe properly. What is given here? What is given here? It is given. 1 minute, 1 second. Yeah. Now listen. What is given here? RCl, RBr given. Logic is very simple. I will replace Cl and Br. So when Cl and Br are replaced, iodine going there, Cl-Br bind with Na, become NaCl or NaBr. Now point is, what is the important concept here? Acetone solvent taken. Why it is important here? Because in acetone, this NaCl and NaBr are getting precipitated. And since they are getting precipitated, reaction will not go in backward direction. So from Le Chatelier's principle, you can answer here, driving force for this reaction to move from RCl, RBr to Ri is precipitation of NaCl or NaBr byproducts in the solvent acetone. Got the concept or not? If I take water, then this reaction will not easily proceed in forward direction, because in water, NaCl, NaBr soluble, reaction go in backward direction. Got the concept? If I want to replace this Cl or Br by fluorine, then what I can take? Heavy metal fluoride, for example, silver fluoride. Generally, water solvent taken will give you Rf, and this Cl will come out as AgCl, or Br will come out as AgBr. Got the concept now? In the place of, this is known as Schwarz reaction, this is known as Finkelstein reaction. In the place of AgF, I can take other reagents like Hg2F2, COF2 or SbF3. Got the concept now? So this is the whole story here. Now you are knowing the concepts, you can easily go for this reaction. BrNaI, solvent not given, but you are knowing solvent is acetone. What will happen? Br is replaced by iodide. I'll get compound here, ethyl iodide. Ethyl iodide. Next is given, the most important reaction. What is given here? Observe properly. What is given here? Br2 given with the light. What concept I said? X2 light or heat given. X2 light or heat given. Compound is given to you. This compound is given. X2 light or heat given. What to break? What to break? CH or... Yes, very good, very good. CH bond. Where? Which CH bond? For double bond? Which CH bond? CH bond at alpha. CH bond at alpha. So double bond, directly attached carbon, alpha carbon. I'll break this CH bond. I'll bind halogen there. Understood or not? So Br2, any halogen, Cl2 given, Br2 given, break alpha CH bond. Sir, if they are different, then no problem. Let's solve this also by this one example. Assume this compound is given to you. Condition is X2H nu. This X2 can be Cl2, this X2 can be Br2. In case of I2, oxidizing agent like HNO3 or HiO3 required. Okay, so I will break X2H nu given. X2H nu given. What to break? CH bond at alpha position. So double bond, this is alpha. Double bond, this is alpha. This alpha has CH bonds, and this alpha also having CH bond. And let's say I have to break only one. So which one I will break? The one who can give more stable radical. So if I generate radical on this upper one, this will be stabilized by resonance of this double bond as well as more number of alpha H. This will stabilize by double bond and less number of alpha H. So which radical is more stable, upper or lower? Which alpha radical is more stable, upper or lower? After breaking of CH bond, which alpha radical is more stable, upper or lower? Answer here, I am waiting. Yeah, upper. So I'll break this one. Okay or not? And by breaking of this one, I'll bind halogen there. So I'll get compound this. Is it clear now? So if I'm concluding finally again, X2H nu given, break alpha CH bond. And if HBr peroxide given, break carbon-carbon pi bond in homolytic manner. And here opposite. Radical motion on left, bind bromine right. Radical motion on right, bind bromine at left for HBr peroxide. Is it clear? Understood or not? Come to the next part. Okay. Next one is... They are saying arrange each set of compound in the increasing order of their boiling point. What is given there? Bromo, methane, bromo form chloromethane dibromomethane, bromomethane CH3Br, bromoform CHBr3, chloromethane CH3Cl, and dibromomethane CH2Br2. In this case, concept is what? More molar mass, more van der Waals attraction, more boiling point. Simple. Next is 1 chloropropane, isopropyl chloride, and 1 chlorobutane. So 1 chloropropane, isopropyl chloride, and 1 chlorobutane. So out of these, who is having maximum surface area? This one is having more surface area. Then this one, and this is having least. So who is having more boiling point? This one, and this one, and then this one. Easy question. Got the concept or not? These are two very easy questions. Okay or not? Okay, you're knowing one concept. If RCl or RBr, or it can be Ri also, reacting with the KCN, another case reacting with the AgCN. In case of KCN, what they will give? RCN as a major product. In case of AgCN, they will give RNC as a major product. Sir, what is the logic? In case of Cn minus, in case of KCN, it is a predominantly ionic. So it will break as K plus and Cn minus. So in this case, nucleophile is a Cn minus. And that's why I can get Cn as a major product here, nitrile as major. In case of AgCN, it is a predominantly covalent. AgCN is a predominantly covalent. Ag C triple bond N. So here nitrogen is carrying lone pair. So this will act as nucleophile, attack on this R, and Cl will leave. So here nitrogen binding with the carbon, that's why I'm getting RNC as a major here. Means in this case, KCN case, Cn minus is the nucleophile, which is giving me nitrile as major product. In case of AgCN, this entire AgCN is acting as nucleophile because in this case, it is predominantly covalent. Understood or not? Understood the concept? This part is clear. Now, if KNO2 given, it is predominantly ionic, so K plus NO2 minus. So that's why it will give you me RONO as major product. But if I am taking AgNO2, in this case it is predominantly covalent, entire molecule will act as nucleophile. Here NO2 minus is nucleophile. In this case, complete AgNO2 is nucleophile. That's why it will give me AgRNO2 as a major product. We can memorize directly also. What we can observe? Ag taken here, N is binding to the R. Here Ag taken, N binding to the R. It means in case of silver, for example, AgCN or AgNO2, nitrogen is binding to the carbon of given compound in the major product. So you can memorize by the trick again. Ag taken, who will bind? Nitrogen bind to the carbon. Ag taken, who is binding to the carbon? Nitrogen is binding to the carbon. Now, if they are asking in case of KCN, why nitrile is a major product? See, nitrile major, so isonitrile minor. Isonitrile major in the second case, so nitrile is minor. Means in this case, Cn is major, so Nc minor. Nc major, Cn minor. Here ONO major, so NO2 minor. NO2 major, so ONO minor. Okay. Now they can ask why Cn is major. Go for the NCERT explanation. Say simply CC bond is more stable than Cn bond. So they are asking why Cn is major here. As per NCERT, we have to answer because CC bond is more stable than Cn bond, and that's how we can justify why nitrile formed as major in case of KCN. Or we can say KCN is predominantly ionic. Okay, come to the next case. In the following pair of halogen compound, which would undergo SN2 reaction faster. So SN2 reaction, you are knowing, is affected by the steric hindrance if halogen is same. So here chlorine, same halogen, go for the steric hindrance. Here this carbon, the carbon to which chlorine is attached, Okay. Okay, chalo. Here question is about the SN2 reaction. SN2 reaction is dependent on the steric hindrance if halogen atom is same. So here, leaving group chlorine same, and this is the carbon to which chlorine is attached. So this is hindered by two groups here, and here it is hindered by only one. So here is steric hindrance more, SN2 less. Simple. Hindrance less, SN2 more. So out of these two, first is having more SN2 in this case. This is having more SN2 because less hindered. In this case, it is carbon iodine bond and this is carbon chlorine bond. Which one is easier to break? Obviously, carbon iodine bond is longer, easier to break, means more reactive. So first is more reactive for SN1 as well as SN2. Okay, so this is given here, answer is given. Here they are saying some compounds are given, we have to find the order of SN1 and SN2. For SN2, what to check? Steric hindrance, and for SN1, what to check? Stability of carbocation. Okay or not? So more hindrance, less SN2. Okay na? So steric hindrance more, SN2 is less. Carbon stability more, SN1 is more. In this way you can find it. Now someone is asking question, sir, out of ortho dichloro and para dichloro benzene, who is having more melting point? So melting point largely depends on the packing, and you can observe packing in para is, see, this is the outer boundary for the para and this is the outer boundary for ortho. So out of ortho and para, this para has more regular boundary, and that's why here packing is better, and melting point of this para is more than ortho as well as meta dichlorobenzene. Okay, so this para dichloro benzene is more having more melting point than ortho as well as meta. Ortho meta almost same melting point. Okay, chalo, move to the next question. Identify chiral and achiral molecule in each of the following pair compound. Okay. In this first compound, chiral center present? Yes. In second compound, these two bromine identical. See, these two are in no chiral center, no chiral center. In this case, OH, H, CH3 on this side, 1, 2, 3 propyl. All different chiral center present here also. In this case, OH is same, but this side ethyl, this side also there. Left, right, same. So no chiral center here, no chiral center, no chiral center. Here you can check for this carbon. This side CH3, one is H, other side ethyl, and down side bromine. CH3 means methyl, ethyl, bromine, hydrogen. All four different chiral center present. Here not present. What is the chiral center? Tetrahedral center surrounded by 4 different atoms or groups is chiral center. This is going to become RD. Now structure of RD given here. D is bonded to this carbon number 2. Means previously Mg was bonded here. So this is MgBr. This is your compound C. Because if I have this structure, carbon, 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 MgBr, then I can write Mg delta plus carbon delta minus. This carbon delta minus bind with the D plus and I can get D to the middle carbon. So based on this product, I can think about the structure of the previous one. Here D is binding to the middle carbon, means previously here in the place of D it was MgBr. Come to the next question. They are giving condition R prime X is going for NS ether reaction. So what we are knowing, Wood's reaction we are knowing RX, sodium dry ether. Sodium dry ether is giving me RR. So now go for the opposite. Now this sodium RX sodium dry ether, RX sodium dry ether is giving RR. So now assume RR given and we have to find RX. How will find? Break this and bind X there. So in same manner, this RX, R prime X is giving me this compound. By which reaction? Wood's reaction. By Wood's reaction. So what R prime could be? So I will break this bond. So this part is my R prime. Got the concept? So basically I can say here this is CH3, CH3X. Okay or not? Now they are giving Mg to this to make the compound D. So this is going to become CH3, CH3, and in the place of X now it will be MgX. This is D. Now what is given? H2O given. So H2O I can write what? H plus and or to go for correct constant HOH I can write delta H plus and OH delta minus. In this Mg is delta plus and carbon delta minus. So this H plus bind with the carbon minus. So this compound becomes CH3CH. CH3, 2-methyl propane is formed. Okay, next question. Polyhalogen compounds, you can read, it is very important topic. Okay, so this chapter completed. Next is alcohols, phenols and ethers. Alcohols, phenols and ethers. Alcohols, phenols and ethers. Alcohols, phenols, ethers. You're knowing if OH is attached to the aromatic ring directly, it is phenol. Not directly attached to the aromatic ring, it is alcohol. And alcohol and phenol, they are different functional groups. If one OH present in the alcohol, it is monohydric, 2OH dihydric, 3OH trihydric alcohol. If OH present attached to the 1 degree carbon, primary alcohol, attached to the 2 degree carbon, secondary, attached to 3 degree, tertiary alcohol. If OH is attached at the alpha position of carbon-carbon double bond, it is named as allylic alcohol. Now it can be primary, secondary and tertiary with the previous logic, attached to 1 degree carbon or 2 degree carbon or 3 degree carbon. If OH is attached at alpha position of this molecule, benzyl alcohol, this is known as benzyl, primary benzyl alcohol, secondary benzyl alcohol and tertiary benzyl alcohol. Means if it is attached at alpha position of aromatic ring, it is alcohol, because not OH is present but not directly attached to the aromatic ring, means it is alcohol. Attached at alpha position of aromatic ring, it is a benzyl alcohol, primary, secondary or tertiary with the logic primary carbon, secondary carbon, tertiary carbon. If OH is directly attached to the benzene, it is a phenol. In this case, if one OH attached, monohydric phenol, dihydric phenol, trihydric phenol. Is it clear or not? Okay. So now I said concept, you can easily identify primary, secondary, tertiary alcohols. Okay or not? Here this OH attached to this carbon, this is primary. So it is primary alcohol. It is a primary alcohol and allylic alcohol. Primary allylic alcohol. In this case, primary. In this case, we can observe this is attached to 2 degree carbon. This is secondary benzyl alcohol. Okay or not? In this way, you can find others also. Okay. Next is this easy part. That's I'm not emphasizing much. You have to read, but you have to solve the question. Okay. IUPAC nomenclature discussed. IUPAC nomenclature discussed earlier many times. One very important concept here. Bond angle of dimethyl ether or ethers is more than 109 degrees. This oxygen is sp3 hybridized. Oxygen is sp3 hybridized. sp3 hybridized means parental angle 109. And usually because of lone pair, bond pair, lone pair, you're knowing lone pair repulsion more than lone pair, bond pair repulsion, lone pair, bond pair more than bond pair repulsion. And that is why usually bond angle is going to be less than 109. But here, because of large bond pair repulsion, even in fact more than LPBP, it is going to be more than 109. It is 111.7 degrees. So memorize directly. In case of ethers, hybridization is sp3. Lone pairs are present even though bond angle is more than 109 degree. For example, dimethyl ether, it is 111.7 degrees. Okay. Come to the question part. Give the structure and IUPAC of the products expected from the following reactions. First is given catalytic reduction of butanol. Al means aldehyde. Butanol means 4 carbons. So this is given. This is butanol. I am not writing hydrogens attached to the carbon. Catalytic reduction. For example, H2 in the presence of Ni, PD or PT given. So this will reduce this CO into alcohol. So this will give me 1, 2, 3, 4 carbon. This become alcohol. So butanol will form. Okay, now butane 1-ol. Next is what? Hydration of propene in the presence of dilute sulfuric acid. Propene is given and reacting with the dilute sulfuric acid. Dilute sulfuric acid, or they can say few drops of concentrated sulfuric acid added. Few drops of concentrated sulfuric acid added means it is a dilute. You can read in NCERT part of class 11th. They are adding few drops of concentrated sulfuric acid added. Means actually it is what? If I am adding few drops of concentrated after going the reaction mixture, this become dilute. And dilute sulfuric acid means more amount of water. So this is used for the addition of water. It is for the addition of water. H2O, H plus. And you're knowing in case of water, H plus is not existing as H plus. It is existing as H3O plus. Existing as H3O plus. Written here. Then story is what? Addition of water. Break pi bond and bind with H plus here. Then same question, where plus charge more stable? You will say the middle carbon. So obviously this will be generated here. Cation middle carbon. Then next step, H2O will attack. And finally, after the completion, I will get here OH in the middle carbon. I will get here propane 2-ol. Addition of water, Markovnikov product formed. Next is reaction of propanone with methyl magnesium bromide followed by hydrolysis. Propanone. This molecule is propanone. It is reacting with the methyl magnesium bromide means Grignard's reagent. In the Grignard's reagent, this CH3 is delta minus Mg is delta plus. Whenever Grignard is given, its first preference is H plus. Whenever Grignard is given, its first preference is H plus. H plus attached to sulfur, H plus attached to the oxygen, H plus attached to the nitrogen, H related to the terminal alkyne, H plus attached to the halogen. These are the preference of Grignard, first preference. So you can memorize like this also, Sona tax. Sona tax. Hydrogen attached to sulfur, hydrogen attached to oxygen, hydrogen attached to nitrogen. Okay. Hydrogen attached to terminal alkyne and hydrogen attached to halogen. These are the first preference of Grignard's reagent. If they are not available, means first preference is H plus. They are giving H plus. If they are not available, then it is going to attack on delta positive center. So now this carbon is delta plus and this CH3 is minus. Minus attack on plus, common sense here. Minus will bind with plus, and this pi bond will break. It become O minus bind with the plus. Plus is here MgBr. So by this reaction, I'll get here adapt CH3, CH3, CH3. This CH3 bind with this carbon. This become O minus, pi bond break, and O minus bind with MgBr. So I can write here O minus MgBr plus. When water added, to make concept easy, I'm writing water as H plus and OH minus to make it easy. This O is minus and this H is plus. Minus plus bind. So I'll get here compound CH3, CH3, CH3. What happened here? Observe properly. This is O minus bind with this H plus. It become OH. Another product, byproduct I can say MgBr plus and OH minus. And another is MgBr OH. So this product is formed 2-methyl propane 2-ol. Got the concept or not? Next one. They are saying, so how the following alcohols prepared by the reaction of suitable Grignard reagent on methanol. So now observe. I will tell you the reaction. You knowing this concept. RMgX reacting with the HC double bond OH methanol. R delta minus Mg delta plus. Carbon delta plus. Minus attack on plus. Pi bond break. It will give me R. This is CH2 O minus MgX plus. By this R bind with the carbon, O become minus, minus bind with the plus. When water added, O minus bind with the H plus of water and will give me RCH2OH. So what I am observing here, if CH2O given, it is CH2O, it is giving me CH2OH. How? By reacting with the Grignard reagent followed by hydrolysis. Okay or not? So now observe, this CH2OH present here. So means previous part, this is coming from the Grignard. So which Grignard reagent is taken here? CH3CH, CH3MgBr. This Grignard taken. And this CH2O coming, I'm going for the Grignard reaction from the CH2O. CH2OH, CH2O. Simple here. Got the concept now? Okay. Any problems there, Ravi? What happened? Okay, next one given H2H plus given. Many times I explain this concept. H2H double bond pi bond break bind with H plus. Where plus motional middle OH bind here. I'll get this propane 2-ol. NaBH4, very important reason. NaBH4 can react with, can reduce aldehydes and ketones. Can reduce aldehyde, can reduce ketones, and can reduce acid halides into the alcohol. Okay. Battery is there. Let's check it once. Battery is there. No problem. Full. This full. Okay. Chalo. So what I said, NaBH4 can reduce aldehydes, ketones, or acid halides into alcohol. So now in this given structure, this is ketone react with the NaBH4, and this ester will not react with the NaBH4. This is not affected. This will react. So after the reaction, ketone part reduce into the alcohol, and another thing means this ester part remains unaffected. If I take LiLH4, lithium aluminum hydride, LiLH4, then it will reduce this ester as well as this CO. Okay or not? Next is given NaBH4. NaBH4 react with the aldehyde, ketone, and acid halide. So aldehyde is available. This will reduce into CH2OH. That's how we can think about the product. Next one. Arrange the following compounds in the order of their increasing boiling point. What is given here? Pentane 1-ol. After
End of the molecular section.
So we have to stop it. Okay, you can stop, no problem.
Okay. Yeah.
Okay, do me. How much time is there?
5 minutes.
Only 5 minutes. Okay, then stop it. Wait, it will be reconnected in few seconds. Okay. Okay. So now, is it done? Okay, chalo, theek hai. All are connected? Chalo. What is given there? Arrange the following compounds in their increasing order of boiling point. First compound given pentane 1-ol. 1, 2, 3, 4, 5 pentane 1-ol. Next given butane 1-ol. Next given ethanol. And next given methanol. So now in this case, this is easy question here. All cases monohydric alcohol. This is having greater mass as well as greater surface area. So boiling point of first is more and this is least, decreasing. This is maximum, this is minimum. Next is given pentane 1-ol. Second is given butane, normal butane. Next is given butanol. Butanol. And next is given ethoxy ethane. So here I will explain you one very important concept so you can easily solve this kind of problems. If you are solving boiling point, then boiling point of 1 minute. I'll explain the generalized concepts you can easily solve. Okay na? Boiling point. I'm assuming molecular mass values are either exactly same or approximately same. Means I can simply answer comparable. Molecular masses are either exactly equal or approximately equal, means comparable molecular masses are taken. Then boiling point of carboxylic acids is more than alcohols. Alcohols are having more than aldehydes and ketones. Alcohols having more value than aldehydes and ketones. Ketones are having more value than ethers and alkanes. In case of ether and alkane, boiling point values are very close. And that is why there is no fixed end. Sometimes alkane is more, sometimes ether is more. I'm saying if molecular masses are comparable, then only this concept is valid. If molecular masses are not comparable, this concept is not valid. Okay. In case of ether alkane, boiling point values are very close. That's why in some cases alkanes are having more boiling point. In some cases ethers are having more boiling point for the comparable molecular masses. So how to memorize? If carbon count is for alkane is 1 carbon, 2 carbon, 3 carbon or 4 carbon, means up to 4 carbons, 1, 2, 3 or 4 carbons, up to 4 carbons of alkane, ether is more. 5 carbon onwards, alkane itself is more. Okay na? What is going to memorize here? Carboxylic acid. In case of carboxylic acid, they are having extensive hydrogen bonding. In fact, in vapor phase they exist as dimer. Because of this hydrogen bonding. That's why they are having high boiling point. In alcohols also hydrogen bonding is possible. Alcohol molecules can also go for hydrogen bonding. Is it clear now? Aldehyde ketones are having lower than this because no hydrogen bonding. Okay or not? And ether alkane are very less here, but out of ether alkane, in some cases ether more, some cases alkane more. How to memorize? Up to 4 carbons of alkane, ether is more. 5 carbon onwards, alkane itself is more. In this way, you can find the trend. Out of aldehyde ketones, if molecular masses are equal, then or almost equal, then ketones are more than aldehydes. Okay, in this way you can find boiling point trend for the different functional groups provided molecular masses are comparable. Got this concept? Is it clear to you? Now you can easily solve this problem. What is given here? First compound given butane. Pentane 1-ol. Pentane 1-ol. Next compound given butane. Next compound given butane. Next compound given me pentanal. And next compound given ethoxyethane. So this is alcohol. Second is butane. Third is butanol. Third is pentanal. Yeah, pentanal 1, 2, 3, 4. Pentanal and everything. Okay. This is alcohol. Alcohol is more than aldehydes and ketone. This aldehyde. Aldehyde more than ether and alkane. Now here alkane given how many carbons? 4 carbons. So who is more? Ether is more. I said up to 4 carbons of alkane, ether is more. Okay, now in this way you can solve it. Okay, understood. Chalo. So that's why I explain generalized concept. If you're knowing generalized concept, you can solve almost all cases by that logic what I said to you. Next example. Arrange the following compounds in the increasing order of their acidic strength. First compound given propane 1-ol. Propane 1-ol. Next compound given 2,4,6 trinitrophenol. 2,4,6 trinitrophenol. Next compound given 3-nitrophenol. And next compound given 3,5-dinitrophenol. Okay. So now observe. Acidic strength order based on functional groups. Maximum for sulfonic acid SO3H, then for carboxylic acid, then it is the phenols, then alcohols, then terminal alkynes, and then terminal alkenes, and finally alkanes. Sulfonic acid, carboxylic acid, phenol, alcohol, terminal alkyne, terminal alkene, alkanes. Picric acid is a phenol, but it is more acidic than carboxylic acids. So here, out of 1, 2, 3, 4, directly one thing you can say, 2, 3, 4 are phenols and 1 is alcohol. So I can simply answer 2, 3, 4 are more acidic. 2, 3, 4 are more acidic than 1. Logic 2, 3, 4. They are 2, 3, 4. They are phenols and 1 is alcohol. In case of 2, 3, 4, you are knowing if functional groups are same, we can solve by the mesomeric and inductive. Acidic strength is increased by minus m and minus I. So now here NO2 minus m, minus m, minus m, 3 minus m. Here attached at meta. Attached at metas will not affect by minus m, but affect by the minus I of NO2, minus I. Here minus I, here minus I. Sir, why you are considering minus I here? Because if group is attached at meta, will not increase the acidic strength by mesomeric effect. It is 0 at meta. So we have to check minus I only. So acidic strength increased by minus m and minus I, and minus m is more powerful than the minus I effect, means 2 is more acidic than 3 and 4. So 2 is more than 3 and 4. In 3 and 4, 2 minus I will increase more acidic strength than 1 minus I. So 4 is more than 3. Got the concept now? So 2, 4, 3 and 1. This is the order of acidic strength. Next example given. Okay. Done. Now question is right, structure of the major products expected from the following reactions. First is given mononitration of 3-methylphenol. 3-methylphenol. CH3, okay, 3-methyl phenol. At 3 position I will add methyl group. So 3-methyl phenol given. Mononitration means what to add there? 1 nitro group, nitrating mixture taken, and we have to go for mononitration. Now here OH is ortho para directing and activating. CH3 is also ortho para directing and activating, but OH is plus M, it is more effective, so I will go for OH. Okay, it is more activating due to the plus M. For OH, this is ortho, and this is a para. So these 3 sites are available. Okay or not? Ortho, para. Okay. I will not prefer this ortho because this ortho is hindered from these two by this OH and this CH3. So I will prefer this ortho or this para. So here I can get one mononitro product where I am binding NO2 at this ortho, and another in which case I am binding NO2 at this para. So here I will get these 2 major products. Important point, I will get 2 major products. One is para position of this OH, another is this ortho position of this OH. This ortho is not least preferred. Why? Because it is hindered by CH3 and OH2 groups. Got the concept or not? So here I am getting 2 major products. One is ortho position of OH, this ortho of OH, and one is para of OH. Why considering OH? Because OH is activating the ring by plus M. CH3 is activating by plus H, and mesomeric effect is more powerful than the hyperconjugation effect. Now they are saying dinitration. So dinitration means what? Bind 2 NO2. So obviously 1 NO2 at this ortho, 1 at this para. If they are saying trinitration, then both ortho and this para. Simple question here. So dinitration, trinitration cases are very easy. Okay or not? Next is give the structure of product you would expect when each of the following alcohol react with the HCl, ZnCl2. These are reactions, very easy reaction discussed earlier only. Let's say we have ROH, and I want to convert this into RX. I can take HCl, catalyst required for in case of primary and secondary alcohols. I can take HBr coming from ionic bromide and sulfuric acid, discussed earlier. I can take HI to get iodoalkane, HI coming from ionic iodide plus H3PO4. I can take SOCl2, best method for the preparation of chloroalkane from the phenol. I can take PCl3, I can take PCl5, okay not? I can take PBr3 and PI3. PBr3 and PI3. They are generated by in situ method. PBr3 prepared by red phosphorus and Br2, and this is prepared by red phosphorus plus I2. So what is given there? Butane 1 all given, HCl, ZnCl2. This is primary, will go for SN2 reaction. So simply in the place of OH I will get chlorine. As HBr given, I will get bromine here. SOCl2 given, I will get chlorine here. Simple question, very easy question. Okay. The next question is predict the major product of acid catalyzed dehydration of 1-methyl cyclohexanol and butanol. So 1-methyl cyclohexanol given. This is cyclohexanol, that's saying 1-methyl, means here only we have to attach methyl group. Acid catalyzed dehydration. So if it is acid catalyzed dehydration, H plus will protonate this, it become OH2 plus. Because of high temperature, this OH2 plus will leave and generate carbocatan here. So we'll give this carbocatan. Now for this carbocatan, identify the CH bond in the surrounding of plus, which are different type. So here, this CH of left and right identical, I will represent one, and this is another. Because of heat, this CH bond will break. Double bond formula, let's say possibility A. Because of heat, this CH bond break, let's say possibility B. So as per possibility A, I will get this alkene, and as per possibility B, I will get this alkene. This alkene, first alkene is having 2 plus 2, 4 alpha H, and this is having 3 plus 2 plus 2, 7 alpha H. This alkene is more stable, means it's going to major product. Okay or not? Similarly, we can solve next question also. Butane 1 ol given. In case of butane and all, acid catalyzed dehydration means concentrated sulfuric acid and high temperature given. What first thing will happen? This OH is getting protonated, it become OH2 plus. Because of high temperature, OH2 plus will leave and I will get this carbocation. It will go for rearrangement here. So after the rearrangement, new carbocation is formed here. Due to the heating, CH bond in the surrounding of carbon will break. So these two possibilities are there. Let's say possibility A and let's say possibility B. As per possibility A, in this case, I will get double bond here, means I will get this compound, this alkene, and as per B, I will get this alkene. This alkene has more number of alpha H, means it is major because more stable, and B is minor here. This is what acid catalyzed dehydration reaction, which is also named as E1 reaction here. Next is what ortho and para nitrophenols are more acidic than phenols. Draw the reaction structure of corresponding phenoxide ions. In case of mononitrophenols, like orthonitrophenol, metanitrophenol, paranitrophenol and phenol. Order of acidic strength is paranitrophenol, orthonitrophenol, metanitrophenol and then phenol. Directly memorize POM phenol, para ortho meta, POM phenol, paranitrophenol, orthonitrophenol, metanitrophenol, phenol. This is the order of acidic strength. Sir, why ortho is less? So in case of ortho, this H and this O, and O of NO2 and H of phenol, they are going for intramolecular hydrogen bonding, and that is why acidic strength of this orthonitrophenol become less than paranitrophenol. So if they are asking question, why orthonitrophenol is less acidic than paranitrophenol, one simple answer: because of this intramolecular hydrogen bonding, removal of this H become slightly difficult, and that is why orthonitrophenol become less acidic than paranitrophenol. Next question. Write the equation involving the following reactions are Riemer-Tiemann reaction and Kolbe reaction. Riemer-Tiemann reaction. For Riemer-Tiemann reaction, substrate is a phenol and reagent is CHCl3 chloroform in the presence of NaOH. This is going to generate dichlorocarbene electrophile. This will bind at the ortho position of this phenol and it will give O, and because of basic medium OH become O minus, and this dichlorocarbene electrophile bind, so it is giving me CHClCl. OH NaOH is taken there. Because of NaOH, this 2Cl will leave and OH bind there, so this compound is formed. Then you know, 2H on same carbon, highly unstable, immediately removed as water, and if it is removed as water, this part becomes CHO. So this is formed, and if acid added, then O minus become OH, so I'll get here this compound. So here, in case of RT reaction, in case of Riemer-Tiemann reaction, possible question: reagent chloroform and NaOH, electrophile dichlorocarbene, substrate phenol, intermediate product is anion of the salicyldehyde, and final product is a salicyldehyde. Got the concept or not? Okay, in case of Kolbe's reaction, what we are doing here, in this case, substrate phenol taken. First of all, we have to convert phenol into phenoxide. In case of Kolbe's reaction, first of all, we have to convert phenol into phenoxide by giving base like NaOH. Sir, why? Because in Kolbe's reaction, electrophile is a carbon dioxide, which is a very weak electrophile. Since it is a weak electrophile, we have to make ring very active. That's why it can react with the weak electrophile easily. It can react easily with the weak electrophile CO2. So here, one important point, they can ask one very beautiful question. In case of Kolbe's reaction, Kolbe's reaction, I'm not saying electrolysis. In Kolbe's reaction, why it is important to convert phenol into phenoxide first? Because here I'm dealing with the weak electrophile carbon dioxide. That's why firstly increase the activity of ring. See, in phenol ring is activated. We have to make it more active. Then react with this ortho and finally give H plus. So what will happen here? This O minus by giving H plus become OH, and now it is a COO. What I am giving here? COO. So it will bind as a COOH. Salicylic acid will form. Okay or not? So this is Kolbe's reaction. Okay, understood. Chalo, next part. Okay, now question is, following is not appropriate reaction for the preparation of third butyl ether. So they are actually asking question based on the elimination versus Williamson's ether synthesis. So always remember, in Williamson's ether synthesis, we can take any RO minus, any alkoxide ion can be taken, but alkyl halide part, RX part must be primary or 0 degree. Alkyl halide part must be primary or 0 degree. Okay, so what will happen? This minus will attack on this and X will leave. And here I am writing 0 degree to make it easy. Otherwise, as per NCRT, 0 degree is 1 degree. As per NCRT, 0 degree is 1 degree. Because NCRT is saying if carbon is attached to one carbon or not attached to any carbon, it is primary. So as per NCRT, if 0 degree given, even though we have to consider that one as primary. Got the concept? Because NCRT is saying if carbon is attached to one carbon or not attached to any carbon, it is a primary. Is it clear? So in Williamson's ether synthesis, alkyl halide must be primary. Or to make it easier, I am saying 0 degree also. So this will attack and X will leave. I'll get ether here, ROR prime. If it is other than primary alkyl halide, then elimination will happen. For example, RO minus taken. For example, this case. Got the concept? So now let's observe. Let's observe. Here, alkoxide ion. See, alkoxide ion is not deciding ki will go for elimination or Williamson. Who will decide? Alkyl halide will decide. Here, alkyl halide, is it primary? Definitely no. So Williamson ether synthesis is not preferred. Go for elimination. Elimination means beta elimination. Chlorine leaving group. Directly attached carbon alpha. Next carbon beta. Remove beta hydrogen. This is beta H. So this O minus Na plus is present. O minus remove beta hydrogen. And this sigma will hit here, Cl will leave, and I will get alkene there. Got the concept or not? So in this case, I will get alkene, not ether. Understood or not? And that's why it is not appropriate for the preparation of this ether. Then sir, what is the appropriate condition? What condition I said? Take alkoxide any. Alkyl halide must be primary or 0 degree. As per NCRT, 0 degree is 1 degree. Okay or not? So here, what is a better condition? This condition. Now observe here. Okay, what is the better condition in this case? Better condition in this case is take tertiary butoxide, react with the CH3Cl. In this case, this CH3Cl cannot go for elimination reaction. So this O minus attack here, Cl will leave, and by this I will get this ether as a product. Understand the difference or not? So tertiary taken, ether is not preferred. Alkene is preferred with the RO minus. Okay or not? Chalo, next condition. This is given. Now observe the alkyl halide. Okay, here it is a primary alkyl halide. Primary O minus attack, Cl will leave. Ether synthesis will happen. Williamson's ether synthesis will happen. Chalo, next one. Physical properties concluded for all at once. Okay, let's observe the few reactions. In case of ethers, ether is least reactive functional group. Ether is least reactive functional group. In case of ether, they are least reactive functional group. So they are reacting with the strong acids HBr or HI at high temperature. First process is this O getting protonated, it become oxonium ion of the ether. Let's say one is R and there is R prime. Three possibilities are there. One is good for SN1, other is good for SN2. Then SN1 will happen. If one is good for SN2, other is also good for SN2. Then you have to find who is better for SN2. How to find? By less hindered. Less hindered will, see, R is good for SN2, R prime also good for SN2. Then we have to find SN2 by the less hindered. Less hindered part will go for SN2. Likewise, SN1, then decided by the stability of carbocation. More stable carbocation part will go for SN1. SN1 versus SN2 here, SN1 is preferred. If it is a tertiary, what will happen? SN1. If it is a primary, what will happen? SN2. If it is giving resonance stabilized carbocation, for example, benzyl or allyl, SN1 will happen. In case of 2 degree, ether is substrate here, ether is solvent also. Here it is polar aprotic in nature. So in case of 2 degree, it will go for SN2. 2 degree will go for SN2 here. So 2 degree part is very important. In case of ether, 2 degree part is going for SN2 reaction. Others are very logical. By 1 degree SN2, you know, in least standard, 3 degree SN1. Resonance stabilized carbocations like benzyl allyl, SN1. 2 degree in case of ether going for SN2. After that, you can easily solve here. What is given? HI given. HI given. First thing, this O get protonated, it become oxonium ion. This is 1 degree. This is also 1 degree. Good for SN2. This is also good for SN2. Who is better for SN2? Answer is less hindered. Who is less hindered? This right hand side is less hindered. This is big group na yaar. S less hindered means here I minus will directly attack on this carbon and this bond will break. So this left part become alcohol and right part become iodide. That's what you can check. Left part is alcohol, right part is iodide. Come to the next case. First step common, this is getting protonated. This part is 1 degree, good for SN2. This part is 3 degree, good for SN1. If SN1 versus SN2 condition given, what will happen? SN1 will happen. SN1 means generation of carbocation there. So this right hand part will generate carbocation. And if I want to generate carbon here, I have to break this bond now. If I break this bond, you can observe this side become alcohol. So left part become alcohol, 1, 2, 3 alcohol. And this side become carbocation. So this carbocation is generated. Next step, this is not going for rearrangement. Next step, I minus attack here and this will give iodide. Okay, next part given. Here you can observe, this is here oxygen attached to the phenyl, partial double bond character present. So this carbon oxygen bond will not break at all. Only one possible break, this bond. Means this part will give me phenol. This is going to be HO because this O remains bonded with the carbon, partial double bond character is present. So obviously if this part become alcohol, so this part become iodide because HI given here. If HBr given, this become bromide. Is it clear or not? Now if they are asking mechanism, so you can check. This part will give me resonance stabilized carbocation. Means mechanism is going to be SN1. Okay, in this way you can solve questions for this part, and this is the most important part in this chapter because oftenly they are asking one question from this ether chapter, from this HI reaction or HBr reaction. Okay or not? Electrophilic substitution reaction very easy. Anisole is ortho by directing. OCH3 is ortho by directing. So binding at ortho or para. Para is going to be major. Ortho is going to be the minor product. Okay or not? So it is also completed. Now move to the next chapter, that is next chapter, aldehydes, ketones and carboxylic acids. Aldehydes, ketones and carboxylic acids. Okay. So for this chapter, before this chapter, I am giving you break of 5 minutes only 5 minutes. Okay. After that we'll start the lecture. Okay. Only 5 minutes. Now is it okay? Audio, video, everything is coming properly? Okay, chalo. Next chapter, second last chapter of the organic chemistry, aldehydes, ketones and carboxylic acid. Memorize these three structures: vanillin, salicylaldehyde and cinnamaldehyde. They are very important structures. Vanillin, vanilla ice cream, you knowing na? Vanilla ice cream, dessert. So okay, that is having flavor, this vanillin. Okay. Salicylaldehyde, this is having sweet meadow smell. Okay na? You can observe your name written somewhere, it is written, yeah, meadow sweet smell. Okay or not? And this cinnamaldehyde is the flavoring agent in cinnamon. Spices are there, one of them is cinnamon. Okay na? So this is cinnamaldehyde. Okay, so higher aldehydes are having fragrance. Okay, higher aldehydes are having good fragrance, pleasant fragrance. They can be used as like in vanillin, it is a flavoring agent there. Some can be used as perfume or solvent in the perfume industry. But lower aldehydes are having irritating or pungent smell. Higher aldehydes are having good smell or fragrance. Okay. Chalo. Come to the question part directly. And as per said, knowing carbonyl compounds are acting as electrophile as well as nucleophile. Now question is, give the name of reagent, bring out the following transformation. Condition is given hexane 1 ol. Hexane 1 ol. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. Hexane 1 ol. 2 hexanal. 2 hexanal. 1, 2, 3, 4, 5, 6. Hexanal. Means here this alcoholic group is oxidized into aldehyde. So I am going for partial oxidation, means I need here mild oxidizing agent. What is required? Mild oxidizing agent. For example, here I can take PCC, or I can go for the condition CrO3 anhydrous. CrO3 anhydrous. One more important point, if it is a volatile alcohol, then I can go for copper or silver 300 degrees Celsius condition also. In this condition also I'll get this aldehyde. If I'm taking strong oxidizing agent, for example KMNO4 or K2CR7, then this CHOCl alcohol will oxidize into the carboxylic acid. 1, 2, 3, 4, 5 carboxylic acid. Is it clear or not? So here I'm going for the partial oxidation, then I have to take mild oxidizing agent like PCC, pyridinium chlorochromate, or CrO3 anhydrous, or for volatile alcohols. For volatile alcohols, you want to make aldehyde from the primary alcohol, then you can go for this condition copper silver catalyst at the temperature 300 degree Celsius. Next one is given cyclohexanol to cyclohexanone. Now in this case it is given cyclohexanol to cyclohexanone. Now in this case this is oxidation reaction. Here alcohol is converted into the ketone. It is secondary alcohol, so oxidation of secondary alcohol will give us ketone. In this case, you are knowing ketones are not easy to oxidize. I'm not saying ketone cannot be oxidized. I'm saying ketones are not easy to oxidize. So here I can use mild oxidizing agent, what we discussed earlier, like PCC or other case discussed there. Here I can use a strong oxidizing agent also, but avoid heating here. Avoid heating here, otherwise ketone will also oxidize. So here if you are making ketone from the secondary alcohol, then you can take mild as well as a strong oxidizing agents, because ketones are not easy to oxidize. And if you're taking strong oxidizing agent, avoid heating, otherwise formed ketone will oxidize and give you carboxylic acid by the carbon-carbon bond breaking. Next is given here 1-fluorotoluene to 1-fluorobenzaldehyde. So now what is given there? Oh, sorry, not one. Sorry, parafluorotoluene to parafluorobenzaldehyde. This is the condition. So basically what we are doing here, CH3 group attached to the phenyl is converted into the CHO group. This is the simple logic. So here we have many reactions. For example, one we can go for CrO3 acetic anhydride condition followed by hydrolysis. Another condition, Itard reaction, we can go for CrO2Cl2 in carbon disulfide solvent followed by hydrolysis. Or we can go for dichlorination, means Cl2H given, 2 equivalent. So 2 alpha H replaced by chlorine means dichlorination followed by hydrolysis at temperature 100 degrees Celsius. This is the industrial method of preparation of benzaldehyde from the methyl benzene. Okay or not? So by these methods I can go for this process. Sir, in this case, why you are taking this kind of reason? Because here I am doing partial oxidation. You can observe here CH3 oxidized into CHO only, not going for complete oxidation. Because if you are taking strong oxidizing conditions, for example KMnO4OH minus heating followed by the H plus taken, then this CH3 will oxidize into COOH. Are you getting or not? So here I want partial oxidizing conditions. That is why I am taking this kind of reagent where chromium CrO3 taken in acetic anhydride followed by hydrolysis, CrO2Cl2 in carbon disulfide followed by hydrolysis, or chlorination, side chain chlorination or dichlorination followed by the hydrolysis. This side chain dichlorination followed by hydrolysis is industrial method of the preparation of benzaldehyde from toluene or methyl benzene. Okay, so I think this is clear. They can ask intermediate also. So just quickly revisit the intermediate in case of Itard reaction and CrO3 anhydrous method. Revisit the intermediate formed before hydrolysis. Okay or not? Next is given there, ethane nitrile to ethanol. Ethane nitrile, CH3CN, ethane nitrile. Now, in case of nitrile group, two possibilities are there: complete hydrolysis and partial hydrolysis. Okay, no, so there are ethanol. Okay, so in this case, first of all, I need to convert this into CH3 CH double bond NH. Okay, this is another question. There we have to make ethanol actually, CH3CHO. Before that, I need to convert this nitrile into imine. How it is possible? Two possibilities are there, two cases are there as per our syllabus. Give SnCl to SCl, which will go for partial, which will help this reduce the Cn into Cl, means partial reduction will happen. Okay, now SnCl to SCl, which will give nascent hydrogen and reduce this nitrile into imine. Or give diibal H, diisobutyl aluminium hydride. They will reduce this nitrile into imine, and if you are going for the hydrolysis condition here, then this carbon double bond nitrogen is available. This carbon CN bond will break, O bind with the CH, and this H2 bind with the NH. So this becomes CH3CHO, and this part become ammonia, and that's why I can make this compound here. Next is given allyl alcohol to propanol. Allyl alcohol. So firstly, allyl means OH present at the alpha position of double bond. Allyl alcohol to propanol. So here you can observe this is alcohol is oxidized into aldehyde. Partial oxidation condition. So can I use a strong oxidizing agent? Definitely no. What to use? Mild oxidizing agent like PCC or CrO3 anhydrous, or if it is volatile, then copper, silver 300 can also be taken. Next, what but2ene to ethanol, but2ene CH3CH double bond CH3 to what to prepare there? Ethanol CH3CHO, means what is required? Break this bond, bind oxygen and bind oxygen. So break this bond, bind oxygen, this becomes CH3CHO, and this also becomes CH3CHO. I'll get 2 moles of this. Now in this case we have to go for ozonolysis, O3 H2OZN. Sir, why ozonolysis? Because if you are giving strong oxidizing agent like KMnO4 and K2Cr27, they will also break this bond. They will bind oxygen, form this CH3CHO, but they are strong oxidizing agent. Here they will oxidize this CHO into COH. So instead of getting aldehyde, I will get carboxylic acid. So here, if I want to break this double bond, bind oxygen to make aldehyde, and you don't want to go further oxidation, we have to go for ozonolysis, O3 followed by H2O in the presence of zinc dust. Okay, this is also done. Come to the next. So they're writing here formula, they're writing a structure of PCC, pyridinium chlorochromate, that you can easily memorize. Okay, next is given, write the structure product of the following reactions. Very important reaction, Friedel-Crafts acylation reaction. Anhydrous AlCl3 taken, so this Cl minus move towards AlCl3. Cl minus move towards AlCl3, so this part will become AlCl4 minus, AlCl4 minus. So this backside part is what? C2H5 C double bond O plus. This electrophile is generated. This is benzene, so this electrophile can bind to the any carbon because all the carbons of benzene are identical. So what I'll get here, PH C double bond O CH C2H5. Okay, now this compound will form. Next condition, I think this part is very easy. Next part is given. I will add structure so better clarity will come. C6H5CH2 twice CD means basically it is a PH CH2 CD CH2PH. This is the reagent part. Another molecule given CH3 C double bond OCl. Okay, just write the polarity, you will get answer. Cadmium is metal, so metal will acquire plus charge, so this carbon acquire minus charge. Likewise, cadmium plus charge and this carbon minus charge. Here this carbon is delta plus, so carbon minus attack on plus. Am I right or not? Any leaving group available there? Yes sir, chlorine. This will remove. This removal, if I am removing it directly, this is trick, not the actual mechanism. Actual mechanism is different. This will attack, pi bond break, O minus form, O minus is returning back, then Cl leaving. That is the actual mechanism. But here I am not interested in the mechanism. I am interested in the product. So easy method, cadmium plus CH2 minus. CH2 minus attack on this carbon, Cl will leave. So what is compound formed here? CH3, C double bond O. This CH2PH bind here with the carbon, CH2PH. This compound is formed. Next reaction. Hg2 plus catalyst and H2SO4 given means definitely is a dilute sulfuric acid. Dilute sulfuric acid means addition of water. I can write H2O H plus, or better to write H3O plus in the place of H plus. Remaining story same. Pi bond break, H3O plus is available, H3O plus available. Pi bond break and bind with the H plus. Then same story. Where plus charge more stable, 1 or 2. Where plus charge more stable, obviously at a 2. So OH bind to the number 2. Carbon and develop there. This will give CH3COH. Double bond CH. This will go for rearrangement, and by the rearrangement I will get CH3 C double bond O CH3. Got the concept or not? Next is given CrO2 Cl2 followed by hydrolysis. Which reaction? Itard reaction. What will happen? CH3 will become CHO. CH3 becomes CHO. Okay or not? One more core point here, they can ask intermediate of this reaction. So when CrO2 Cl2 given, what will happen? Intermediate is very important for the Itard reaction and CrO3 acetic anhydride reaction. Here CrO2 Cl2 given, what will happen? This CH bond will break. How many CH bond? 2 CH bonds will break. And CrO2 Cl2 bind there. So CrO2 Cl2 having 2 oxygen, 1 bind here. What left? 1 chromium. What left? 2 chlorines. 1 oxygen and 1 H of the CH bond left, which is also bind with the chromium. This is the one part. Likewise, another CH bond will also break. Oxygen of CrO2 Cl2 bind with the carbon. What left? 1 chromium, 2 chlorines, 1 ONH. This is intermediate compound formed there. Now, if I am doing hydrolysis, this O hydrolysis done, this OO become OH and 2H on same carbon unstable, and this becomes CH. This is NO2 group there in the given compound, NO2. So after the hydrolysis, this become CHO and this is NO2 remains unchanged. So by this concept, what I am explaining here, they instead of asking the final product, they can ask intermediate of the Itard reaction or intermediate. This is brown colored chromium complex. Next one is, okay, chalo, next problem. Here I will emphasize one point. Observe here. Boiling point of acetone is given. Boiling point of acetone given 329 and boiling point of propanol given 322. Propanol CH3 CH2 C double bond OH and acetone CH3 C double bond O CH3. What I said to you, boiling point of alcohol. See, alcohol is maximum here. Alcohol is more than aldehydes and ketones. So 373 more than 322 and 329. Out of aldehyde ketone, if molecular masses are same, then ketone is more than aldehyde. That's what you can check. Acetone more than propanol. After that, what I said, ether and alkane. Ether alkane depends on the carbon count. N-butane given. Carbon count for alkane 4. Up to 4 carbon, who is more? Ether is more. See, ether is more. Provided molecular masses are comparable. Because in ether and alkane part, boiling point difference is very less. Okay, so if molar mass of someone is more out of ether alkane, that is going to dominate. If molecular masses are comparable, then only this story is valid. Up to 4 carbons of alkane, ether is more. 5 carbon onwards, alkane itself is more. Okay. Okay, next is, so with the same logic you can solve this problem also, what I said for the boiling point. Okay na, here alcohol given, alcohol more than aldehydes, alcohol more than aldehydes. Now ether versus alkane, 4 carbons of alkane, and here ether given, so 4 carbon of alkane, ether given, but here you can observe molecular masses up to 4 carbons of alkane, ether is more, and ether has more molecular mass also in this case. Big difference. That's also giving me same answer. Okay or not? Chalo, next part. Arrange the following compounds in the increasing order of their boiling point. Same concept here also. Molecular masses are comparable. Ether, alcohol is more than alcohol is more than aldehydes. Ether versus alkane. 3 carbons of alkane. Ether is more. Up to 4 carbons of alkane, ether is more, provided molecular masses are comparable. Okay, chalo, next part. Easy question, next part. They are asking here ki out of aryl aldehyde, let's say we have this CH3, CH2, CH2, C double bond O, alkyl halide and aryl halide, who is more reactive for the nucleophilic addition reaction? Both are aldehydes. So who is more reactive? So in this case, this is delta plus, this is also delta plus. In this case, this is plus I group to decrease place I, and this is resonance effect, which is affecting the delta plus. So here effect of resonance is obviously more effective, and because of more power of the resonance effect than inductive, this is going to be less reactive. Means out of aryl halide and alkyl halide, aryl halides are less reactive to the resonance effect. Okay or not? Next question. Next, yeah. An organic compound A with molecular formula C8H8O, molecular formula given C8H8O, form an orange red precipitate with 2,4-DNP. You know, in 2,4-DNP test is used to characterize or to find the presence of aldehyde or ketone functional group. So it is giving positive test, means it is having either aldehyde group or ketone group. This part is done. Then they are saying give yellow precipitate on heating with iodoform. So you know, with iodine in the presence of sodium hydroxide, means iodoform test. Iodoform test given by CH3CO, here bad living group like HR or pH, and CH3CHOH, bad living group HR or pH. So DNP is going to confirm that this is CO group. Now they are saying iodoform test is a positive, giving yellow precipitate. Give yellow precipitate on heating with iodine in the presence of sodium hydroxide. Means one terminal is definitely CH3. One terminal is definitely CH3. If it neither reduces tolerance or failing solution, I mean this is ketone, not recognize the bromine water on Bayer's reagent test, means not having carbon-carbon double bond, means not having alkene or alkyne system. So now observe here, C8H8 given, out of 8 carbons, 2 carbons gone. Out of 8 hydrogens, 3 hydrogens gone, 1 oxygen also gone. What left finally? 6 carbons left. But 8 are there, 2 used, so 6 left. 8 hydrogens are there, 3 used, means H5, C6H5, means this part is phenyl. And they are saying also that bromine water test is negative. Bromine water test is positive for alkenes and alkynes. So they are saying bromine water test is negative, means this part is not having alkene or alkyne system. And benzene is not giving bromine water test due to the aromaticity. So this is your compound. This is your compound. Now what they are saying, on drastic oxidizing condition with the chromic acid, it gives carboxylic acid. So now drastic oxidizing condition means a strong oxidizing agent and heating. Drastic or vigorous oxidizing condition taken. This ketone can also be oxidized. What I said, ketones are not easy to oxidize. It means in vigorous oxidizing conditions, ketone can also be oxidized by carbon-carbon bond breaking. Here, this bond breaking will not give me anything, because if I break this bond, this part cannot write carboxylic acid. But if I break this bond, this part become benzoic acid. This will give me PHCOH. This part will give me formic acid, and formic acid oxidize further into H2CO3, and H2CO3 break into H2O and CO2. So this benzoic acid is formed here. Okay, so this is done. Come to the next part. Question is, arrange the following in the increasing order of their reactivity towards nucleophilic addition reaction. First is given ethanol, CH3, C double bond OH, ethanol. Whenever solving any organic problem, always write structure first. After writing structure, problem become easy. Like in physics, you are making free body diagram and everything, so it become easy to understand. In same way, organic problems are also solved, becoming easier after writing the structure. Ethanol, next is written propanol, CH3, CH2, C double bond OH. Next is given propanone, 1, 2, 3, propanone. And next is given butanone, CH3, CH2, C double bond O, CH3. Reactivity of aldehydes and ketones towards the nucleophilic addition reaction is controlled by electronic factor and steric hindrance factor. If delta positive charge on this carbon is more, reactivity more. If this second is steric hindrance, if this is more hindered, steric hindrance is there, so reactivity is going to, steric hindrance more, reactivity is going to less. So reactivity of carbonyl compounds controlled by two factors. One is delta positive charge, means electronic factor, more delta positive charge, more attack of nucleophile, more reactive. And second is steric factor, more steric hindrance, less reactive. Obviously, if steric hindrance more, attack of nucleophile become difficult. Based on this, we can easily answer that aldehydes are having a small hydrogen atom. So aldehydes are more reactive than ketones. Aldehydes are more reactive than ketones. How to compare these two? This is CH3 hindrance and this is ethyl hindrance. This will hinder more. More hindrance means less reactive. Got the concept? Here both are ketones. This one side CH3 common in both. This side hindrance given by methyl. This side hindrance given by ethyl. Ethyl is bigger. More hindrance in ethyl part means less reactive. This is the order of reactivity. Got the concept or not? Next. That's why I consider steric effect and electronic effect. That's what I said. In case of aldehydes and ketones, reactivity is affected by the steric hindrance and by the electronic factor, means delta positive charge on carbonyl carbon. Now given is benzaldehyde. Let's write the structure. Benzaldehyde. Second structure is given para-toluene aldehyde. Para-toluene aldehyde. Next molecule given para-nitrobenzaldehyde. Para-nitrobenzaldehyde. Para position is having nitro group. And next is having acetophenone. Acetophenone. Now observe. Here, first three molecules are aldehydes and last one is ketone. So aldehydes in general are more reactive than ketones. So we can say 1, 2, 3 are more reactive than the fourth one. Now in this case 1, 2, 3, aldehyde, aldehyde, aldehyde. So go for the electronic factor here because hindrance factor is more or less same, because these CH3 and NO2 they are very away. So we will not provide much hindrance. Go for electronic effect. Delta positive charge, delta positive charge, delta positive charge. NO2 is minus M. So we'll withdraw electron density. So delta positive charge will increase. Here CH3 is plus H. It will give electron density. Delta positive charge will decrease. And here no group attached. If plus charge is more, attack of nucleophile more. Attack of nucleophile. If plus charge is more, nucleophile can easily attack there. Means reactivity of third is more. And second is minimum out of 1, 2, 3. Got the concept now? So here out of 1, 2, 3 and 4. Based on aldehyde versus ketone, I said 1, 2, 3 more than 4. Out of 1, 2, 3, maximum positive charge present in third. More positive charge, more attack of nucleophile, means 3 is more than 1 and 2. And in 2, delta positive charge decreases. Plus charge decreases, means attack of nucleophile is becoming less. So 2 is less than 1 and 4 is least because of the ketone. Next, predict the product of the following reactions. Total time pass reaction. You can observe here. What is given there? H2NO. Acid catalyzed reaction. This O and this H2 removed as water. And if it is removed as water, I'll get oxime here. I'll get compound oxime. Double bond NOH. This oxime is formed. Here this H2 and this O removed as water. It is a 2,4-dinitrophenyl hydrazone. I'll get 2,4-dinitrophenyl hydrazine. This is 2,4-dinitrophenyl hydrazine. I'll get product 2,4-dinitrophenyl hydrazone. So your formed compound is going to be double bond NH. 2,4 position is having NO2 group. So given compound reagent was 2,4-dinitrophenyl hydrazine, compound is 2,4-dinitrophenyl hydrazone, and this 2,4-DNP is used in the identification of aldehydes and ketones. Next one is given. So this is very good question. Here we can have, this is NH2 and this is also NH2. Out of these two NH2, which one we have to select for the removal of water? This is very important. So observe here, lone pair of this nitrogen is delocalized. That's why this is less available for the reaction. And here lone pair of this nitrogen is localized, so more available for the reaction. So in this case, if you want to remove water, select the NH2 who is having localized pair of electron. So this is delocalized, less available for the reaction, localized, more available. So they take this oxygen and these two H and remove water, and you'll get the product here. So product will be R CH double bond CH. CH double bond, and this N is used here. So N, NH, and then it is a C double bond O, NH2. Got the concept or not? In this you can write the product here. Next one is, this is a very easy question. What will happen that this O and this H2 remove water, you will get the product here. Understood or not? Okay. Next is carboxylic acids. IUPAC name I'm not going to discuss many times. Okay, so move to the reaction. Which chemical reaction to effect the following transformation? What is it? This is already discussed. Butanol to butanoic acid. I said earlier, na? Butanol to butanoic acid means I want to oxidize alcohol into acid. I need strong oxidizing agent. For aldehyde, I need mild oxidizing agent. Like butanol to butanol, PCC. Butanol to butanoic acid, strong oxidizing agent discussed earlier. Benzyl alcohol to phenyl ethanoic acid. Benzyl alcohol. This is benzyl alcohol to phenyl ethanoic acid. Phenyl ethanoic acid.